So such technology will be help ensuring safe exploration as a foundation for the future lunar navigation satellite system. So our mission objective, we use two 60 CubeSats. Each one have 11.7 kilogram and will be deployed in the low lunar orbit. So we have a two mission object is on the radio occultation and radiation environment. And we have a three extension mission object, radiation with the space weather and atmosphere, orbit determination, and range measurement. Great. So before our mission, we focus on the simulation of our instruments. So radio wave through the plasma medium, we all know the phase space. So we map. We can know simulation is scale high. Is a model. We can see the radio waves through the will be cause a delay. If we use a dual frequency, that can carry, and we can reveal the electron density. And here we also analyze the differential phase delay, and you can see the tangible of the like electron density. Okay, great. So what's the difference in our proposal compared to the previous mission? Yeah, there are some mission already do the radio occultation, but their measures a path to the Earth. So there will be measures the atmosphere, capturing only fringe of the lunar region. And our methods allow for border measurement over the lunar without interface from the Earth atmosphere. So resulting more precise and resembling in space. And you can see they are also very large satellite. But we can use also use a frequency. So we can achieve lighter and because we use a lower frequency for the electron density. Okay. Also, we radiation environment model to predict instrument performance under the different states where like this one is a take this event for example. So we have particle propagation, and you can see similarly the electron and photon dose rate, including the total dose rate. Sorry. And with the shielding effect, read data, we can refine the model and has the particle. Okay. So we have two pillars. The first one will call occultation of arranging integrate orbit determination. So there are before you can see the architecture. They use the OBC to control time clock, and there will be generated per second signal to the B205 minute. And that stabilization between the oscillation of the both SDR. And they transmit the signal from the UHF and VHF, so they are low frequency. In addition, Orion takes of the so we can analyze the orbit dynamics through the double shift. So to perform in the arranging of the specific GPS PR encoding waveform. Okay, this is our second pillar. We call it deep space radiant probe. And here have a two mission object we mentioned before, but mostly you have to measure the radiation dose and single event offset rate. And only is a RAD-fast sensor and the NAND flash memory chip. We use a payload control to read the data. So based on the low, we choose the orbit is 1 kilometer low lunar orbit, and with like 86 inclined, because this is a quasi mitigate the perturbation from the even gravity field. So we choose this polar region, and we deploy the CubeSat is a forward and here's our SDK analysis. This attitude changing, the CubeSat changing due to his 1 year. And so you can see it will keep changing and was in the lunar surface mission and tangent point of the rock path to the lunar surface. So you can see the rising, the 0, the 100 km high, and without the maneuver. We mentioned the two situation that the satellite is too far, it cannot be the occultation performance. So in our scenario, we use a real satellite, the yellow one, and temporarily changing to the eclipse one, the yellow, and then changing back to the yellow one circular orbit. And around we take a day, and so it can move ahead of the leading satellite. Okay. So here's the orbit strategy. We follow the Koshiba protections. So we're prevent the contact environment. So like a calorie that we will avoid to the lunar polar region, also including the region. So will be the orbit at a subzone, and will be touched for 30 DOV and crush at 51 north flat. So based on all the payload and the orbit, we have 8 operation mode, including emergency and the normal mode. So you can see a chart about the power and TDNC when the CubeSat lie outside the ground station, and Samsung when the two CubeSat can see each other. And propulsion mode is when the reaction well saturation, and heating mode when the CubeSat in the when the eclipse region to manage the temperatures and before. So here's our CAD model. The most component are choosing for NASA Silver. So here have a high TRL, and science panel you can see right place right here. So right here is can expose the chip, so measure the radiation. And here's some subsystem like a thermal control technology 4 panel with the multi-layer insulation, and also equip the 2 panel about the zero coat Teflon tab as a radiator. And we have a EPS marginally 30%, proportion mode have a 68% and 49% in the different, and the jump flash to avoid, and also you can see the different routing configuration. So here are our implementation plan. Right now we're in our phase B, and in the phase E we have to mitigate only the 3 eclipse, the limit exposed to cold environment from the 2027 Q4 to the 2028 Q4. And our human resource students, so the total cost roughly the $430,000 US. Recently, we have conducted primary research, including 3D model and the aerobarrier testing. And here our risk matrix shows our main risk is a loss of position, but we can minimize based on the transmission, and also have insertion funding and the technology transfers. So through this project, we hope not only to expand the human knowledge of the moon, but also to explore the 262 CubeSat for more understand the lunar atmosphere and radiation environment. So our strategy is to align the design in payload design house, and also is a student lead team with creativity and association provide a great flexible control in achieve our goal. So ultimately, we should align SDG 4, 9, and 17 further advance the human cell validation.
Okay, time is.
Thank you very much.
Thank you very much. Okay, now question by the review team.
Thank you for the presentation. I read your paper, and it's not clear to me from your paper how you're going to do momentum unloading of the wheels with just 4 cold gas thrusters. Can you perhaps explain how you're going to do momentum dumping of the wheels in 3 axes gas thrusters?
So we place the cold gas nozzle in the 4 place, and we will do our algorithm to make sure that can can stable the control. So I will do our algorithm to do that.
So you're going to unload plus or minus in one axis for 3 wheels, each one in a different axis with 4 cold gas. That doesn't sound possible to me. You need at least 6 cold gas thrusters to unload the wheels, positive or negative.
Oh, for the freedom of maybe 6 axis, yes.
Do you agree?
Yeah, I agree. with
Okay.
that.
Oh, wait, about that, we actually placed not the total direct. You place like a 45-degree, so we can try to unload the reaction. But maybe the professor will try to keep deep research about this. But okay.
Okay, thank you for the very nice presentation. And I have a question about the Orion SDR payload.
Yeah,
I think you mentioned that the TRL is 3. Do you plan
Yes.
to increase this before the mission? What's your plan for that?
Manage the risk. Okay, so we actually keep updating this idea to make sure that can be true, because like we actually have a more, the main risk is the oscillation. You know, play the G-scale time clock stable, the 2 CubeSat that have a 2 SDR, right? I try to back to quickly. Sorry. Okay, it's too much. Okay, yeah. We actually, main risk is oscillation problem. We also have a stable 2 SCR. We also stable this one. Main risk is how to synchronize this 2 time to we actually have a this is last year right here. This is based on another paper, is a synchronous one-way range. The key point is adding the 2 so divide the 2 cancel the offset that the 2 CubeSat can be in the same time, so we can measure the more precisely. So this is our, based on our know and our research, is a high risk for us.
Yeah.
Okay, thank you.
So thank you very much for your good presentations. So I would like to ask about the requirement. So requirement for the accuracy of electron density measurement and requirement.
You mean the performance or?
Yes, so measurement accuracy of this.
Oh, measure the accuracy. Well, about this measure accuracy, not an analysis, but we do some ranging analysis. We know, yeah, it's like the same question, and that be unstable, and that might be causes the phase delay will be have an error, and so the differential phase delay might be also have an error. But that part we are not yet. We try to do analysis, so make 3 can be 4 and 5 keep going up, but we just right now just a very perfect simulation, not counting the error and including the oscillation. So yeah, we will keep going that, but the performance, you can see the tangent point altitude, you can see the differential delay, like we choosing a red line, so roughly it will be measured depending on the altitude. Yeah.
Is not the actual performance, but how accurate you should measure this. How precisely to measure?
Oh,
Requirement.
requirement. Really writing requirement about measurement because just I mentioned the lunar is mark. So we didn't write and say, wow, what kind of measurement or you know, but that go in, but we proved there's a no answer over there. So we didn't write about this payload the requirement, what it need to do. We just want to understand whether there's on the moon or not, because there might be pop out somewhere, not like the Earth. Real Earth is covered the whole day everywhere. So we didn't really write down the requirement for them. Yes, but we do some range measurement or orbit measurement. That part we do, but about ionosphere, no, we just try to explore this. Yes.
Okay.
Okay, thank you very much.
It's okay. Okay. So it's a very quick, short question. How about do you, manage the orbit? Because on the lunar orbit, there is much, and
Yes.
even if you put it in the quasi frozen
Quasi
orbit,
frozen,
it
yeah.
moves. And how you can manage the orbit?
Yeah, indeed, quasi frozen orbit, but this perturbation from the lunar on gravity to try to maintain. You can see our maneuver, but why to let them really apart from? Because we want to make the radio wave through the habitat to lunar surface. Have to so that can be measured the lower altitude. So if they are set apart, will be catch bad user strategy. But if they are on orbit, there may like a oscillation something. We'll try to let them that. It's fine because we do not see about the tangent point. We still can be measurement. We let them random just not focus on the moon. Is that be thing that would be okay for us?
Okay. Thank you.
Well, thank you very much.
Thank you, everyone. If any idea can follow, we want to update this project. Thank you.
Okay, please take your seats. Now, the second is from the University of Sydney, from Australia. The name is Seleni. Please. Okay, please start.
Okay, welcome. We are Selene, a group of 5 undergraduate students from the University of Sydney, Australia. So as humanity continues to explore space, the moon has been proposed as an ideal testbed for long-term deep space habitation. A sustained reliable maps of local resources, such as water, ice, and minerals, to reduce reliance on Earth resupply and become a basis for self-sustainment. We also need to de-risk human activity on the moon, since lack of a magnetic field means that lunar isolation than on Earth, leading to health complications such as increased rates of cancer and reproductive issues because they get no warning about these lethal solar events. There is also an existing data gap since no mission currently provides high-frequency regolith composition analysis rate inside the lunar exosphere. We want to push a move from monitoring to prediction, since existing Earthers cannot support autonomy on the moon, and so in situ forecasting is an absolute prerequisite for deep space habitation. Small CubeSats are more economical and provide higher revisit rates and reduce mission risk. There are 3 mission objectives. The first is to map the lunar regolith composition to derive water ice composition and fresh ejector maps to inform lunar landing sites. The second is to quantify the radiation environment inside the lunar exosphere and compare this to display exospheric absorption and astronaut radiation risk models. The third is to demonstrate constellation-based radiation early warning capabilities. From the radiation monitoring, we will fuse the Selene data with existing solar observatories and exosphere models, which will enable us to increase safety of Artemis EVA missions and future deep space missions.
The operations of Selene will be split into data collection, processing, and transmission. Designated points will be determined on the ground and transmitted regularly to the OBC, specifying at which time to capture an image. At these points, the image spectra will be captured by the HSI and stored before transmitting to Earth. Radiation collection and processing will happen simultaneously. Performance is defined in terms of successful payload operation. The key is fine spectral resolution, so regular mineralogical variations can be properly mapped. This also means minimal image blur is required. The radiation sensor needs to be able to detect low to medium energy, such as solar winds, ejections, and flare events. Each satellite is an identical 2U, equipped with payloads. We have a modular system design configuration, making manufacturing, development, and integration easier. Each satellite has an expected lifetime of roughly 12 months, coinciding with the expected time in orbit.
So our primary payload is a hyperspectral imager that covers wavelengths from meters. We've intentionally designed the HSI to function with no moving components. This helps to reduce complexity and limits potential single failure instances. A thin slit is provided, is placed in the optical train to produce one spatial dimension, which is then split into a spectral dimension using a diffraction grating, and then is focused on the camera sensor. Style camera relies on the way the satellite itself moves through its orbit and uses the orbital motion to trace out the swath. There's a strong precedent with a TRL of 6 and is based on the OpenHSI module developed by the University of Sydney and the Australian Centre for Robotics. The same project influenced the choice of a CMOS sensor over a CCD to limit issues with blooming artifacts and bad columns. The proposed spectral range includes OH groups and infrared spectrum absorptions like a scissors bending vibrational mode at about 1630, and as well iron oxides have distinct absorption peaks within 500 to 1600 nanometers. So we developed a prototype HSI with the same design and then reproduced an image of a building at the University of Sydney. So on screen we have the original image on the left with the 62 spatial dimension spectra, and then the reconstructed image on the right, which we use to validate the 60-kilometer swath at 100 kilometers.
Traditional methods to measure radiation levels, such as Geiger counts, rely on fragile glass components, which are not suited to the harsh space environment. Solid-state PIN measure the energy of incoming radiation. Instead, the produced voltage response is proportional to the energy imparted by the impinging, and so an energy result spectra can be produced. On screen, you can see a sensor with a width to record the measurements of a red LED as a proof of concept. This data will be cross-correlated with Discover and Go's radiation observatories and their measurements to isolate the effect of the lunar exosphere on the radiation absorption of incident solar flux. This enables validation of radiation models, which feed into astrophysics estimates and mission planning. For deep space travel, existing Earth's models cannot be relied on, and so our constellation provides a pathfinder to develop content-based radiation early warning forecasting systems for autonomy of Artemis and Mars campaigns.
Attitude will be determined through a combination of inertial measurement and sun sensing, fused in a state estimator. A combination of reaction wheels and cold gas propulsion will provide full 3-axis attitude control. The reaction wheels will be primarily used for pointing maneuvers, such as nadir pointing for our HSI, propulsion for desaturation and DT. The onboard computer will be the Isospace OBC, which importantly has 32 gigabytes of data storage, allowing us to easily store spectra.
The satellite will be powered with a conventional solar array and lithium polymer battery combination. Solar array will triple junction cells in a 2-series 4-parallel panel configuration. It's a maximum power of 18.44 watts at the beginning of life. To supplement satellite operations during eclipse and in high power operating modes, a 30 watt hour LiPo battery is used, capable of providing an instantaneous wattage of 12.1 watts. Power through the system is managed with a power conditioning and distribution unit that provides 3.3, 5, and 12 volt rails.
So Alim will use the EnduroSat S-band stack due to its cost effectiveness and has been optimized for our payload requirements. We will have two main channels of communication with downlinks, direct to Earth for command, control, and data, so direct to Moon for radiation early warning and data to support future. For direct to Earth communication, we will be using the deep space network. Many missions will be utilized for max coverage. This table shows the worst case link budget for the Canberra site, and as we can see, achieve a maximum data rate of 50 kilobytes. The Lunar link budget has also been calculated. This is based on a goal of landing for Artemis. This ground station uses Yagi style antenna, and again, we have sufficient link margin to actually increase our data rate if we want. The orbital parameters can be seen on screen, and Selene has been designed with a Walker star configuration with 3 equally spaced planes, each with 2 satellites, so 6 satellites total. This setup allows for full surface coverage in just 9 days. And we have above Earth over 1 gate to Earth.
So the project began earlier this year with the development model, complete testing of the flight model in 2027, with sort of ready to launch by the end of 2027. The expected cost is about 3.8 million, that's Australian dollars, primarily due to launch. The testing, as you can see, is zero because the University of Sydney has a lot of facilities to test. The risks we identified, there were 5 key risks, developed a mitigation strategy for each, which brought most of them down. However, the one medium risk is insufficient propellant to regularly desaturate the reaction wheel. However, oversize the wheels so to hopefully minimize the effect of that being required, and have some contingency propellant just in case.
Based on systems engineering and methodology, we developed an engineering model to validate that, which Charlie is passing around to you now. We developed this model at a small budget of 1,500 Australian dollars to skill up the team, our payloads as a proof of concept. All subsystems have been extensively tested across a range of conditions and success criteria. Overall, Selene payloads will support sustained habitation of the lunar environment through enhancing resource location capabilities and by providing a safety net to astronauts that helps mitigate the considerable presented by extreme solar activity. Thanks very much, everyone.
Well, thank you very much for your presentation.
Satellite is a 2-unit CubeSat. On it, you want a hyperspectral imager, as well as 10.1 degree sort of pointing accuracy. That is quite challenging for a 2-unit CubeSat. How are you going to fit all these subsystems in a 2-unit volume? If I look at your table 2, it doesn't give the various sizes of the components that it can fit into a 2-unit CubeSat. You have a reaction wheel module, for example, there, but in your model that you just showed us, the wheel is quite big. Can you fit 3 wheels in one in each axis in that sort of volume, that purple volume?
Yeah, the model has 3 wheels, 1 in each axis. There's also a little bit of space above the reaction wheels.
So that model contains all also the hyperspectral imager?
Yes, the only subsystem that it doesn't contain is the cold gas propulsion system, because we didn't have the budget for that, you know.
And that's about 0.3 of a unit.
Yes.
And you need to detrade your.
Yeah,
I believe the module we chose has 6 on it.
It has 6. Okay, it's not the MIPS, IMIPS unit.
Yeah,
with 4 nozzles.
Oh,
yeah.
Okay, so thank you very much. And I'm curious about the altitude control. Maybe you corrected how much disturbance is coming, right? In order to make this what is the strategy to this situation?
Okay, so given that we're in a lunar orbit, we expect that there's no perturbation due to like magnetic field. So the only that we're expecting, and also no aerodynamic drag as well, because there's no atmosphere around the moon. So we're expecting only a sort of gravity gradient perturbation torque. Shoot are quite small, on the order of 10 to the -5, I believe. So that will be accounted for in the closed loop control. In terms of desaturation, we aim to do that without alcohol gas propulsion.
So you did that?
Yes.
Okay, thank you.
Yes, sorry, that was the other one. So those are on the order of 10 to the -5.
Thank you for the nice presentation. I have attitude determination. I think you mentioned IMU, how you perform attitude determination.
So IMU, it's a freedom IMU. So we have accelerometer measurements. We also have sun sensor measurements as well. So we fuse them in a filter to obtain the attitude estimate.
Three attitude determination, not just the sun sensor. It's only one vector. Rotation vector you can't measure. You need another sensor and vector measurements. Yeah, it's still measuring the same sun direction. Yeah, I'm is feet per second, so there's a lot of noise and drift in IMU of that range. So your measurement noise is at least 10 milligrees per second, or it's 1 degree per second.
Thanks for the presentation. Very nice to see some hardware that you've presented today. In your mission as addressing a move from monitoring to prediction. So do you see this as a one-off mission or something that we can see? And would the constellation still exist when there is a human presence on the moon?
Yeah, so the idea is that this would be an ongoing mission. This particular mission has a span of 12 months, which is governed by as well as the lifespan. But because of the cost and the sort of each satellite is exactly the same. So we'd be able to keep them replenished and keep lunar habitation on the moon to then keep up this radiation forecasting throughout lunar presence.
Have you given consideration in that to a scalability and a plan from doing one-offs to sort of batch production or frequency production of these systems?
At the moment, we've only considered a constellation of 6 satellites, and in terms of our implementation plan, it's only been sort of 6 as an initial feasibility to prove the technology. in that initial year-long mission, and then from there we'd look at upscaling it.
Yeah. Especially since Artemis isn't really looking to get people, well, I say they are, but get people landing on the moon, what, 3 years? Like maybe in the next 10, we can put another constellation up, or, I mean, keep it going until then, but yeah. Thank you.
Just a question about, you said there's orbital decay, but you said there's no atmosphere around the moon. Where does the orbital decay come from?
The orbital decay comes from the irregular gravitational field of the moon.
That will not decay, it will just oscillate more in altitude. Decay means it comes closer to the moon.
Yes, so according to
over time.
Yeah, according to my research, I found studies from NASA that showed that for certain orbital parameters initially, the orbit decays to the surface.
Sorry, there will be another presentation later this afternoon about dust particles around the moon. So you have collision against those dust particles, and that decays the orbit. So there is a area around the moon. It's not nothing. The moon has gravity, so there will be some sort, maybe not the same as density as the Earth's atmosphere.
Okay, thank you very much. Okay, the third team is from South Africa, Isilimela Space Systems, and the mission name is Reason 1, I think. Well,
hello. Okay. All right. So, everyone, my name is Dirk Slabber, and I will be presenting our concept rover mission called Rover for In Situ Umzi-Ingeni, or Ryzen 1. The name is derived from one of my country's languages, Xhosa, and Umzi-Ingeni roughly translates to moon village. So, the last decade has revived interest in the international space, and it, unlike community, is concerned with permanence, as seen in the Artemis missions that plan to do so in the 2030s. This poses an interesting challenge for engineers, however, as there is now a need to rapidly establish feasible solutions for habitation and sustainment of human life. A major aspect of this is the in-situ gathering, processization of resources such as water, air, fuel, food, and electricity. 3 of these resources, however, could be extracted from lunar ice. The Ryzen 1 mission then is developed as a series of missions to perform resource utilization experiments on the moon, starting with understanding or improving understanding of the regolith ice itself. Specifically, the mission's main goal will be to conduct a subsurface heating experiment for the purposes of understanding the heat transfer capabilities. It comes as a pleasant surprise then that in preparing these slides, I found that the Indian Space Agency conducted a very similar experiment during the Chandrayaan-3 mission in 2023. This indicates at least that the Ryzen 1 mission objective is relevant. Then, breaking the main objective in smaller objective, the goal of the rover's first goal would be to deploy and explore the area. Find the ideal spot to perform the experiment, but to take pictures of the lander and the lunar environment to engage the public with. Once it's in, possibly a small shaded area, the rover will drill 2 lunar regolith some distance apart. After this, the experimental heating and sensing should be installed in those halls, and the heating experiment conducted. During the experiment, the heating unit will simply emit heat to the surrounding regolith, while the sensing unit monitors the effects of the heat over the span of a few hours. Finally, the rover should perform the necessary distribution as in the article. As an additional objective, however, while not operational, that drastically affected is that all the above needs to be achieved technology before 2030 in order to keep up with the timeline set by the international community. To develop a rover in this time, our team proposes retrofitting a CubeSat docking mechanism developed by Stellenbosch to allow the rover to have a swappable payload system. The rover then becomes a generic carrier for the payloads, who will each be designed as an independent unit. Using this method means there will be 4 payloads developed specifically for navigation, heating, sensing. During the mission, the rover must dock onto a payload on the module of the lander, go and perform the relevant mission objective, and then swap out the payloads once again. The lander, it's then of focus for the mission. Only does the lander provide communications between the rover and Earth, but it also acts as a power source payloads, the rover docking mechanism, and the experimental payloads during the heating experiment. So, and to meet the objective of rapidly deployable technology, instead of developing a rover from scratch, it is built from commercial off-the-shelf CubeSat components. In doing that, the development time reduces and can rely on the space heritage that these parts followed the design of the Astrobot quite closely due to the similarity in size and weight class. And from this design, the rover had a 2U CubeSat structure housing all the generic components. The final weight of the rover will be just under 6 kilograms, leaving an average 1 kilogram per payload. The table on the right shows all the components of the rover. Those that can't be bought, such as the wheels or the motor drivers, must be developed. Communication to the rover proved an interesting design exercise, as it would remain a single point during the exploration process. And to ensure communication, the rover is outfitted with 2 UHF whip antennas for telemetry and an antenna for imaging. As the design continued, analysis such budget were conducted. However, due to the uncertainty regarding both the lunar environment and the rover, the practicality, these analyses proved to be quite superficial. So and in the interest of understanding of the rover operational requirements, a rover prototype was built. And while this system is not intended to be a hyper-representative as an theoretical analyses. The rover was built using a Raspberry Pi and camera system, 3D printed parts, and various subsystems from an educational satellite kit, much like our Heptasat kit. Able to Wi-Fi, take sensor, short range. We conducted operational tests in a dry riverbed, where the white sand is intended to mimic soft regolith. These tests highlighted design inefficiencies, such as inadequate suspension and the lack of slip awareness. And these should be points of focus for the second design pass. Prototype was a time-consuming task, but it was an excellent opportunity and learning experience. It recreates a process that will undoubtedly be carried out numerous times during the development of the actual rover. So given the objective of investigating in situ resource utilization for habitation, its site also be located on the southern pole of the moon. These regions are targeting a greater percentage of regolith ice due to the greater occurrence of permanently shaded areas. In addition, some of the high altitude features experience near permanent sunlight, allowing incredible energy harvesting potential. 2 areas are to the Horizon 1 mission. Firstly, the Shackleton de la Grande as the planned site for the Artemis base. Then here would be ordinary exploration and environmental analyses. The second area is the Munsmaton mountain nearby. This mountain was the planned operational area for the Viper mission that was cancelled, but also aimed at analyzing regolith ice. It should be noted, however, that landing in this area is quite difficult and treacherous. Area can mean a permanent or and a less risky option might be to land in a really flat area, for example, close to the admins and the actual implementation of the mission will involve various stakeholders and collaborators executing on the NASA satellite that the rover slots that cannot be developed as academic lunar environment act as advisors. The role of agencies and lander providers such as iSpace cannot be stressed, and they will have as they will have the means to provide ground stations, the lander itself. The rover aspect of the mission is determined to cost in the ballpark of $7 million, only possibly coming from an agreement between us to fund this mission as an academic undertaking. The main risk to the mission then is not getting all shareholders aligned or them losing interest. So with that in mind, I'd like to conclude the MIC9 mission, and ultimately the opportunity to engage with these problems present a unique learning experience that has certainly been instrumental in my development as an engineer. Thank you.
Okay, thanks. This was quicker, so we'll have more time for questions.
Now ADCS questions, Paul.
No, give me, I will try a power systems question.
Okay.
You said your power system design was quite superficial, but I couldn't really find anything about sizing of the battery, sizing of the solar panel. You had one table saying what is the power managed or power requirement in the different phases of the rover's application. Can you say something about why did you choose a 2-unit CubeSat solar panel, for example?
Okay, I feel that there's two questions here. To start with, we never went into full power system design. I rather meant that the power budget analysis proved quite superficial due to the wide range of operations that the rover will be operating in. And I think that's where the prototype, the analysis from a prototype is more viable to actually get that initial data from which you can make proper decisions. Why we decided on using a 2U then, because we estimated on using commercial off-the-shelf components with a standard, say 40 watt-hour CubeSat EPS, this seemed in line with what we estimated our power requirements were going to be. The solar panel, I think we relied more heavily on the idea that the lander will be able to power the rover or recharge the rover via the docking mechanism. And so I think I stated in the article itself that the solar panels will only act as a real backup power and not be the main input source of power for the rover.
So the rover needs to return to the lander to recharge.
Mm-hmm.
So do you have indication of how long it can spend on its own during a worst case hard terrain mode, for example, so that consumes 15.5 watts of power? How long can you then go with the size of battery you have and the solar panel you have charging the battery? You're at the south pole, so solar conditions is not perfect. Your sun is coming in at a very low angle. So there's lots of things to consider when you size your battery and your solar panel. I just found it missing in the paper. That's what I'm saying.
Thank you. Yeah, we did not do those analyses, but I can see the worth of it.
Yeah, thank you for the very nice presentation, especially seeing the model was very impressive. Nice work. I have a question about the docking mechanism. So you mentioned that this was developed for a CubeSat. So I guess they have 6 degrees of freedom. They can align themselves quite freely. But in this case, your rover and your lander may be more constrained. So how can you ensure successful docking between your lander and your rover?
Yeah, so delving into the design of the actual docking mechanism itself, there was a surprising large margin in which simply applying a force, there was quite a large tolerances that still allowed the docking of the two systems, which is where I originally thought this could be a plausible solution. However, you're right, if there's a rock, for example, in the way and the one wheel shifts, the misalignment could cause serious issues. With that, I think it falls into the territory of the design of the docking bay, which we unfortunately couldn't spend that much time on. However, how I theorize that you'd probably want some type of ramp deployable from the docking bay itself, from which the rover can possibly align itself quite well to the docking mechanism. That's the only feasible way I could really think of in making the system work. Yeah.
Okay, makes sense. Thank you.
Thank you very much. Just a question on some of the budgets that you've put in, the costs in the budget that you've put in. So you've noted that you'll be developing some payloads in-house, one of which is the drilling mechanism or the drilling payload. Do you see that you've covered enough in terms of the price to ensure that you'll capture all of the activities that are necessary to de-risk any potential issues you'll have with that? A failure of the drill, for example, how will you guarantee the reliability? You've got a lot of prices here and they're all the same. Every payload that you're developing in the house has got the same price. So I just wonder if that is going to cover everything.
As I said, the payloads or the things that will be developed will be done as academic projects. So the students just have to sweat. Yeah, I see where you're coming from. However, in terms of the payloads, because they're not, I think the mission can still carry on if the payloads fail. Yes, if the drill fails, it's certainly a big issue, but not any more than if the heating payload or the sensing payload fails. So I can imagine from academic perspectives that universities will probably allocate the same cost of this. I think what the budgets that is shown in this article would probably be a first draft, and then with proper analysis of, after seeing the preliminary design proposals of said payloads, there can be a reallocation. However, I suspect each payload to still cost roughly in that ballpark.
Yeah, I've seen that in the development budget as well, second for the whole mission, you've got a margin multiplier of 2, which takes the cost from 3.5 to 7 million. So
yes,
that might cover it.
Okay, thank you very much. And I'm curious about the drilling machine. So your rover has a drilling machine, right? Maybe so it's very difficult to do a drill on the moon because the land is very, how can I say, solid, very, how can I say, tough to come into the soil. How you can do that? Because the weight of the rover is not so big. And in that case, maybe if you make a drilling, the rover is coming up. How you can solve the problems?
We estimated that it would just take a really long time to actually perform the drilling test with very consistent, very fast drilling. Drilling without applying too much pressure to the regolith ice itself. That's all. That's my answer. Thank you, Paul.
Okay, thank you very much.
Yeah, thank you very much. So, if I understand correctly, there are some previous mission concept doing a heat transfer experiment on the moon. So what is the difference between the previous missions and your idea?
So I only found out about the Indian space company or Indian Space Agency performing this mission, as I said, as I was preparing these slides. As far as I understand from there, and I did not look too deeply into their experiment. As far as I understand, their experiment focuses on localized heating. So they have an injector rod from the lander itself. You might even be able to see it on the picture. It looks like one of the struts of the lander, to be honest. And this rod itself, I believe, allowed some of the regolith to pass through the outer shell of would then heat particles, and then anyway, and analyze the effects of this localized environment. We believe on drilling holes, say 40 centimeters apart, for example, and analyzing how the heat travels that distance. I believe that has a lot more application, especially to the use of the regolith as resource on the moon in the coming year.
Okay, thank you very much. Okay, the fourth presenter, again from University of Sydney. The name of the mission is SATI, an AI-based space mission. Okay, start please.
Hello, everybody. Our mission is at GPT, and we will be investigating the efficacy of commercial off-the-shelf hardware AI onboard small-sat missions in intense radiation environment. Background is that currently there's a large reliance on data transmission for Earth. The current model is that low level process data. Now, this has two main send data down, constraints how much communication windows for mission space. NASA's MO that highlights this, with over 100 gigabytes of data being produced a day, 4% can physically be sent down to, or OBP, can potentially solve some of these problems, as this reduces bandwidth strain and allows for improved storage optimization. And I guess our thesis for our presentation is that continued development of COTS hardware is promising for small sat missions, with affordable hardware being able to perform this on board, allowing for the affordability for small sat missions. Now, the efficacy in low Earth orbit, such as FISAT and Spaceborne Computer 2, having multiple years using off-the-shelf commercial hardware. However, it's a hardware beyond low Earth orbit, ionizing dose and single event upsets causing damage to hardware. However, the impact of radiation in lab environment has been studied by a number of universities, implying the potential for this use however, the impact of COTS radiation on COTS AI hardware has not truly been tested in deep space.
As part of its payload, it's carrying a dosimeter and a commercial off-the-shelf AI. By measuring the performance of the using the quantified commercial off-the-shelf AI. We've chosen an auto location task for the satellite, where it photographs the lunar surface and tries to locate itself based on the surface features. Involves running neural fault-aware to identify crash. Earth of the AI supporting future space missions that also. So to achieve this, we have 3 key objectives: surface and run an onboard convolutional neural net, identify the ray and positions of the craters. For location, we compare these craters to a database of known and infer the satellite's most likely location. And finally, we run a control neural network on Earth and compare these with the results from the satellite to evaluate the AI performance.
Regarding the choice of the neural processing strategy, we've elected to use the Halo accelerator. This choice allows us to leverage Halo's specialty in direct camera feeds and video feeds and inference models on them. It is computer Pi 5 and it allows for a test bed for us to test familiar machine learning frameworks and then deploy them in a Halo executable file. Its low power consumption as the intensive neural network shown, we believe that an appropriate application for the grayscale crater detection. The objective of the neural network is to locate the craters and identify them. A study of this is shown by the Indian Space Research Organization in the Chandrayaan-2 mission, shown here in this image. The satellite will traverse over the surface and feeding the camera live feed through the key feature ADI and their relative crater center in the frame.
So this is of the Halo 8 integration and implementation. So we begin by training a framework. This then gets to the binary compiler so that the chip loaded and it's live and ready for use. Moving on to the bigger flow dam, the network receives the input from the and performs crater detection and identification, and then it implements the algorithm for detection. Test this against the sun sensor and IMU and star tracker, and against the dosimeter. So to support SatGPT's mission, we're using ArduCam 4.7 high resolution, compact inside, compatible with the OBC, and achieves outcomes of 1. And we're also using it's normal high dose event differentiation. It's compact in size and also has really good space grade design.
So how are we going on how we're actually testing our performance parameters? So key objective, we have our 6-degree estimation accuracy. So this is using 6-degree of freedom, and it's using this equation of picking that compared to our other onboard determination system. We also have our crater recognition IOU, which is the average intersection of the union for all craters that have been detected, that ranges from 0. We have the measurement of reliability of the crater detection as well, each based on identification accuracy. And from there, we can get a full scale implementation and accuracy from our ground station, which is a combination of these 3. So our concept operations, first deployment, which is dispensing, system initialization of our solar panels. We then have image capturing, capture the surface of the moon. From there, we have our onboard processing, which is that now doing our determination using those onboard crater identifications. From there, we have our Earth transmission, which is using the deep network as well, and also on our ongoing Earth-based experimental validation. So that's just running our CNN off. And from then, we have our end-of-life deorbit, which is a controlled deorbit into the surface of the moon. And from there, we would expect our mission would last around 12 months based on research we've done.
Okay, so moving on to our subsystem design. Here we have a schematic which reflects our proposed architecture and the communication interfaces between our subsystems. In terms of SatGPT's overall structural design, we've taken a redundant and modular approach. So the subsystems are enclosed by a 3U aluminium chassis, which provides mechanical support and ensures structural integrity in launch, deployment, and operation. The structure is designed to withstand vibrations and thermal extremes whilst minimizing mass. In terms of SatGPT's solar array, we have 2 deployable faces, which are released via a burn wire and pogo pin mechanism. These ensure maximal exposure to sunlight to meet the higher power requirements of the onboard AI. The onboard computer, so as we've said previously, we've chosen the Raspberry Pi 5 for its computing power, price, versatile interfaces, and its size. For SatGPT's attitude determination and control subsystem, we have 2 main modes of operation: detumbling mode, which allows us to achieve stability, and pointing mode, which allows us to point toward the sun for charging and an antenna at the earth for communications. This is a schematic of our subsystem, which demonstrates how our sensors are fused with an EKF, and we use PID controllers to actuate motion wheels and our thrusters.
So just giving you a quick overview of our electrical power systems and TNC subsystems. So our EPS will be using a lithium-ion battery as well as a solar array to put everything together. So you can see our budget here and how that's all been. And what we found perfectly is all mission states after deployment observe a positive power margin with the exclusion of this prop demonstrates that our CNN can be run at any concerns of major battery drain. We go over to our TTNC, X-band antenna and XTX receiver, and our link budget can be seen here. The whole idea that we want to engage from this is by using our onboard AI processing, our data send rates go from roughly 68 minutes to a massive improvement and really.
So this is our organizational approach and timeline. The mission will be delivered through a partnership between the University of Sydney and Quaver, which will allow the SatGPT team to stay developing our payload models and making sure we mission objectives, whilst we can draw on Quaver's experience and their launch heritage, especially their specialized testing facilities and ground station. The biggest about is our current progress. So we've already developed a low-cost engineering model using just a budget of 1.3 USD. We've already proven in concept, so applying our crater detection CNN, and it can run on the Halo 8 and Raspberry Pi with limited power resources. Next slide. It'll be around 2 million as we ensure that all systems are successful and are measuring the success of just the payload. Upper launch costs around 5 million, which is a very high estimate, but based on depending on rideshare availability.
So as with any great mission, we have a risk mitigation strategy. These have been split into technical and I guess project management based kind of risks. So you can see our main ones are the technical ones and our missions are outboard. So thank you very much for having us. We'll now take questions. We appreciate it.
It's good to see your team believe in gender equality. I've got a question on your ICES. You expect a lot from the ADCs, especially if it weighs 50 grams. That is possible. Small ADCs doesn't exist anyway. But in any case, your position truth, you rely on the ADCs to supply that. How will it work? Can of your satellite to compare the AI results to.
Question about our attitude determination that's independent of the network?
Yeah, attitude, yes, you can do with sensors, you can determine the attitude gyros, determine the rates. How are you going to determine satellite? Using
100%. Like we said, ultimate truth, but limited to get a complete satellite's position. We are just using what we have on board, which we believe is the most accurate reading that you compare. The technology that we're using on board using that CNN is quite novel, and it's only been tested in Earth things. So comparing that to what we have on board with our separate ADC measurement that we do have to
use the the craters and the shape size of this to determine your position. You need a certain for your camera. And you have view angles and you have shadows. Have you taken all that into account in your neural network to compare to a catalog of size and shape of
that we can our AI on different distortions as well. There's a large data, especially maps, so we can take those topographic maps and also generate more data to train out on using like essentially and use to expand our database and use different angles and distortions to basically make our CNN circumstances.
I'll also jump on that. We plan on using to ensure that you can have skew of approximately 10 degrees, such as detecting circles. It can also detect ellipses relatively accurately.
With to compare your AI result, use a position truth that you say you will get from the ADCS. What is the true position of the satellite in the orbit? ADCS cannot give you position information. GPS receivers can give you position, but you don't have GPS receivers around the moon.
I think one part of how we're going to, I guess, know the truth location of the satellite is also by using ground-based simulation. The initial position of the direction it's headed in. We can use ground-based simulation and tracking, validate where the location is. Similarly, this is a validation technique, but it is something we could investigate. Data coming through of the estimated position of the satellite aboard. That can be an initial, I guess, test of where is it to begin propagating that simulation to identify it.
So your ground-based, is it on the moon ground-based or on Earth?
Earth.
Okay.
Yeah. Similar questions. So as to the attitude, also you will estimate your attitude, and that will be compared with the truth, right? True attitude.
That it's directed towards the moon, it's, I suppose, less of a concern than position. But yeah, ideally
attitude.
So it won't be, basically, we've got the two systems. We've got our regular ADCS system, which we have developed, and that's what we'll be using to compare what we've developed with the CNN position, if that makes more sense. So from our CNN position, we can get 6 degrees of freedom of location and orientation of our satellite. There's been quite a few papers on developing those systems. And then we would compare that to what is currently used, which is our ADCS system that we have separately.
Okay. So the another question is that maybe on the moon area radiation effect, if something like a hang up occurs in your computer, how you can countermeasure with that?
Sorry, could you repeat the end of the question?
Yeah, to something like occur for the satellite, and then computer system will hang up or something. Yeah. Stop.
I guess first thing we'll start with is that part of our mission objective is to use relatively low cost COTS hardware that could fail, getting the feasibility. But to circumvent that, we want to use relatively simple processes to harden and protect against. So things like watchdog timers can be used to kind of reboot. Similarly, if I jump back to here, this is not necessarily a single event. Training, sorry. There's a paper from Cornell in 2020 that looked into or proposed this method of training CNNs, where in the training you actually give randomized matrices that kind of scramble the data, turn off neural nodes, all that kind of stuff, or it is actually put into place such that it is significantly hardened against errors from radiation. So that's also part of, I guess, what we're looking into is can fault-aware training be used as a mitigation for hardening against radiation-induced upsets?
Okay, so maybe the one choice is to implement a very, one, CPU, which it has don't has a much against the radiation, very small, and that will monitor all the other, computer. And if something like happens, it will reset this, computer. It's a very, very effective way. So please consider that.
Thank you very much for the insight. Thank you.
Thank you for the presentation. My question was, I think, almost answered there, but just for clarity, that GPT core, your CNN module, how sensitive or susceptible is the system to any errors which are emerging in one or another, and how can you handle that? If something is happening in the Raspberry Pi and there's a single event upset, are you robust against confusing where that event is occurring, and how can you prevent that influencing the results and the CNN system?
That's a fantastic question. So the CNN and the Raspberry Pi Halo et al. Are incredibly close together physically. So while it's not, massive, it means that they're very interlinked in our training. So the identification of the trait creators is going to be computed by CNN, which is largely based on the Halo 8L, whereas position is more algorithmic and database checking on the actual OBC links. So we want to, I guess, clarify, will there be error on not just the Halo 8L, but also the OBC? So a lot of our training with the faultware and the AI accelerator, as well as OBC hardware, such that it's kind of a dual system where both things are being considered for feasibility, not just the CNN accelerator. That answers your question.
Okay. Will you pre-train this in some?
Yes.
Okay. Thank you.
Okay. Much. Okay, the last team for the first session is again Froji, and the mission name is Tilda. Please. Okay, start please.
Hello? Oh, good afternoon. So I'm In Liao from National Taipei University of Technology, Taiwan, on behalf of the TILDA team. And we would like to thank the UNISEC Japan and MIC9 reviewers for, thank you. Oh, okay. Oh, thanks. Yeah, that's better. Thanks. We would like to thank the UNISEC Japan and MIC9 reviewers for having us here to present our mission idea, TILDA, Taiwan-India Lunar Dust Analysis, which is a 12U CubeSat orbiting the moon to investigate the lunar dust particles and zodiac exosphere. So we know that there's no air on the moon. The surface is bombarded by tons of meteoroids and interplanetary particles every day. These impacts not only makes dust ejecta plumes, but also makes local vaporization and ionization of the surface materials. So these for the key driver of the volatile evolution on the lunar surface, especially in the permanent shadow regions, PSRs, and for the zodiac exosphere. We can observe the meteor impacts, like here, as lunar impact flash from ground telescopes, and like this animation here. But it's very difficult to observe the high latitude meteor impacts, and not to mention the PSRs. So So in order to understand the long-term evolution in polar regions, we must have the information of the high latitude meteor flux first. And this can only be done by the in situ measurements by lunar spacecraft. Actually, in 2013, so NASA's Alim mission has successfully identified the dust at around 20 to 100 kilometers above the lunar surface. So this is one of their main results. But the orbit was constrained in the equatorial region due to their mission design, and which indicates that the dust in the vicinity region of the lunar polar region still remains uninvestigated. So therefore, we propose this mission to fill in this knowledge gap, and also because the dust particles are very sharp and attaching destructive to instruments and astronauts on the lunar surface. So our mission results may also benefit the future lunar polar missions. So we have 4 main mission objectives, and the primary and the most important one is to identify the size, the velocity, spatial distribution of the latitude polar region of the moon. And the second is to monitor emissions from the lunar sodium exosphere, including its spatial variability and temporal changes under varying lunar conditions. So this is one of our modeling results showing the sodium exosphere. And the third is to establish the possible correlation between lunar exosphere and the dust environment. And the last one is to demonstrate the technology capabilities of CubeSat at low lunar orbits. Is that the spacecraft will go with polar orbit at around 100 kilometers above the lunar surface. So when the spacecraft enters the lunar night side, it turns to the science mode. And with the 2 payloads, the dust detector and the optical camera will be turned on to do dust and sodium exosphere observation. The second half of the orbit, which is about an hour. And when the spacecraft travels within the day side and is having the Earth in the line of sight, it turns to the telemetry mode for data transmission. In between the science mode and the telemetry mode, there is the charging and idle mode for battery recharge and health monitoring. And after the telemetry mode, we may have the propulsion mode for momentum compensation. The key performance parameters are the science requirements of the tubes. So for the dust detector, it should be low particle sizes from micromillimeter to submillimeter. And it should be able to achieve sensitivity, which is sufficient to detect impact energies on the order of 10 nanojoules. And the third is it should be capable of high temporal resolution, such as 0.1 count per minute. And for the optical camera, it should be equipped with a narrowband filter with a sensor wavelength of 589.3 nanometer with 3.5 nanometer sodium emission D1 and D2 lines. ECAM 50 from Alim system detector, we choose the piezo dust detector, PDD, from the Baylor University in United States. So if you have heard of the Marlin space, U10 series camera are all spaceflight heritage. But for the PDD, it has not been proven yet because its related mission, unfortunately, low Earth orbit, so it has no updated information since then. So, we have some, okay, and this is the layout of our spacecraft design. Since we have very limited time for presentations, so design subsystem very quickly. So these are the details of our subsystems, and so the most important point is that our CubeSat is the 12U CubeSat with a total mass just a little bit less than 14 kilograms. And these CNDH and ADCS subsystems. And this is the propulsion system, the MIPS with the radiation shielding. And this is the EPS subsystem with also the radiation tolerance instrument. And also our power budget. So you can see that we have enough, we have great power addition, more than the power consumption, which means that our EPS system can supply power to meet this at all times. And this is our TNC subsystem, and they're all lunar flight heritage. Okay. Also, the TNC budget for uplink and for downlink. Okay, so we've also done thermal analysis for our spacecraft and our modeling, and will show that spacecraft can stay within the survival limits in sunlight and eclipse. And most importantly is with passive thermal control is already enough. And this is our orbit. The first phase is the Earth-Moon transfer, which includes 6 steps. So from the launch vehicle takeoff, and the launch vehicle and spacecraft separation, the TLI maneuver, translunar cruise, the insertion, the last is the lunar CubeSat deployment. And the total delta V is 4.2 kilometers, and this cannot be done by CubeSat. Obviously, we need to have a mothership for piggyback. And the second phase is the low lunar orbit. This is our spacecraft. The orbit altitude, as I mentioned, is about 100 kilometers above the surface, and the inclination is 90 degrees because we orbit, and the orbital period is about 2 hours. And this is our implementation plan. So we enter India because we have Indian partners in the team, and they have connections to the training ground. So we may have the chance to piggyback the training ground for spacecraft. Analysis. So to summarize, the Tilda mission will enhance the polar dust science and to build the dust exosphere connection and to demonstrate the mineralized technology, and then to strengthen the Thai-Indian partnership for the Artemis era. So thank you very much for your time.
Okay, that was very timely too. Thank you much. Please, for reviewers.
You mentioned that your dust detector must detect up to 0.5 millimeter dust particles. What will happen to the satellite if it collides with 0.5 millimeter dust particle flying at thousands of meters per second? Will it not destroy the satellite? I mean, it's quite a big dust particle, 0.5 millimeter. What is the energy in the dust particle?
Because we're just calling out our engineer because he's not here. But yeah, sorry. You were saying that what will happen if the dust particles are too large?
If they become 0.5 millimeter in size and you collide one of those particles, what will happen to the satellite? What will happen to the orbit of the satellite? The drag will be immense.
The dust detector may be destroyed. Yeah, that's possible. And but in terms of the momentum, actually we calculated just a second. But that's more for because the dust particles may be charged due to the lunar surface. And so actually we have had one very nice question from the reviewers before, in the pre-MSC9, saying that what will happen if the ionization of the dust particles can have some disturbance attitude. to the orbit control. And we've done some calculations about that, but we found that the perturbation will be actually very small. Because due to the so we've done some like plasma simulations, and the potential of the spacecraft will just about like 30 volts, minus 30 volts, and in terms of the orders of magnitude, the perturbation, the influence of the perturbation due to any orbit will be like we can almost ignore that.
Yeah, I think you need to further analyze perhaps your impact of dust collisions to the drag and the decay of your orbit over the life of your satellite.
Sure, we'll take that.
It just seems to me if you talk about 0.5 millimeter dust particles, that will have a huge influence on the orbit, the decay of the orbit. If it doesn't destroy your satellite, it may have a huge influence in orbital decay.
Okay, thank you very much.
Thank you for the nice presentation. I have a question, maybe more about the science objective. You mentioned that you want to measure velocity and mass of particles. I guess your sensor can measure the energy during the impact. So how can you differentiate between mass and velocity?
Yeah, actually, those particles are very slow because they are coming from the impact jet. I think the velocity
I see. But in one of your objectives, you mentioned you wish to measure the velocity of the particles. Very critical? Or?
Yes, we can. But anyway, we can assume some size distribution, and we can measure and we can calculate the and then we can calculate the velocity.
Okay, got it. Yeah, thank you.
Is to simultaneously the dust environment and the film emission from the surface. So my question is, what kind of knowledge are you going to acquire by observing these phenomena?
So what do we need to obtain the dust particles and the sodium exosphere?
So why do you want to know that? Why do you observe Simon? Why do you want to do this mission?
The reason. Okay, so it's because the main purpose is the permanent shuttle regions because we still have like almost like very limited information of that due to because they are hard to act, also because it's impermanent shuttle, so it's basically non-observable just using regular optical instruments. So we want to use this actually
Yeah, I can answer. Because we know those permanent shadow region, we have a lot of water there, but because those water is come from or explanation, and they are the water there, but there is one major loss mechanism, which is the meteor micro impact. Very important because those of those parameter, the water on the moon.
Okay, so and beyond that application which you will be to acquire from this mission. So for example, do you have any application for future human explorers around the moon? So, so is that just a scientific mission or some kind of additional motivation?
this mission only, if we have this mission, it only can tell us some evolution water on the moon, because we measure the meteorite impact, the flux of meteorite coming from outside, and with this we can measure. I think we can, with this we can know where those water coming from, and we know evolution water, and in the future how many water we can use on the moon. But for some local, I don't think with this mission can know the local information from, yeah.
Thank you.
Thank you for the presentation. Looking at the distribution of dust particles in size, that distribution will be exposed to, what will be the exposure that you'll have, what fraction of time, and will that be enough significance? You've got an impact rate of up to 6 per minute for a certain size of particle. What fraction that spacecraft be exposed to?
Yeah, here shows on the right hand side, you can see the impact rate of our 100 from the surface. So for different, a bit different orbital phase, different impact rate. Like the highest impact rate is about 2, so it's quite useful. So during I think 2 per minute.
And is that, your spacecraft will?
Yes.
Okay.
Yeah, this is from the simulation. So actually, we don't know what is the dust environment there. Mm-hmm.
Validated that is enough to be
this one is from a model from previous lattice detection. So basically, on the moon, we have a higher impact, meteorite impact on the downside. So you can see on the, like in the yellow, the 6 is the 6 on the top downside. So we have a higher impact rate of we have a density of the dust cloud. But our goal is to measure the dust environment on the polar region. So I think the cloud density is lower than the downside.
So we have the time over. Do you have a question? Okay. Please be back in 20 minutes at 3 o'clock sharp. Thank you. Aslan さん、半尾今入れちゃう？後でまとめて、もうこれ最後の点だけ、これいらなくても最後 OK ってだけでいいで。ああ、そっかそっか。これとこれ、わかりました、わかりました。で、プレゼンテーションも100点ね。あ、わかりました。僕はこれ全部ペーパーでやってた。はいはい。わかりました。
今、少し
いやいやいや。
ちょっとここに回されパスが進んできた時のエレベーションを確認したんですけど、13度でできた時と21度ででき始めた時があって、今日の1個、この間の度でできなくても、可能性があった
ってことね。
パスだったのかなと。
明日の6.5は期待できるか。だから今日の夜の70何歩でできたら、まあ、それに近いこともないけど、期待するってこと。一番やるよね。
夜なんですけど、一つ目のパス5.5度で、
もうやめる。
は無理だと。
じゃあ、やめて、後ろに寄せてくる。
はい。
いいよ、いいよ。
で、22時19分からの。
だから、どれぐらい集合
?21時50分。
で、間に合う。21時50分。はい。じゃあ、皆さんそれで来てもらって。で、鍵あるから大丈夫だよね。もう70に直接来て。はい。了解。はい、わかりました。21時50分ね。はい。いや、今日の夜のテストを、1つ目のパスはもうやらなくて、2つ目のやつで22時何分でやるから、21時50分に集合。21時50分。10 minutes to 10ね。で、そこから22時。よろしく。あれだよね。アンテナ見えるかなっていうのちょっと気になるけど。あれをライト持ってた方がいい。よろしく。OK。Yes. After the corona. Now, let's see. Okay. I don't. There's a need for it. Yeah. So much.
We have actually 8 subtopics, and we will go over all of them in detail. First of all, while discussing our mission and our design perspectives.
一回それは。いいですね。カメラのいっぱいオフにして、カメラのオフにして、ちょっと喋って、あ、一旦で、あ、そうですね。
あれ、私は今映ってます。
はい、映ってるんです。
Elif, can you speak?
Yes, I'm here.
マイクで喋るのです。
フィンガーアウトテストだから、スクリーンで、ちょっと待てよ。そうか。あ、やっぱでも無理か。これだと、この画面、待てよ。これしか出なかったんですよ。だとすると、向こうにしないとダメか。つながないとダメですね。
じゃあやりましょう。
すみません。ちょっと、なので、そうすると、この画面が出るので、
インします。
そうですね、これオン、
イン。
ピン、そうです。
はい。 喋ってもらえますか。
そうですね。カメラと一応あれを。
Elif, can you turn on your camera?
Is it better?
Yes.
Yeah.
あ、で、声が、音声が。
音声が、なんかちょっと。
Can you speak something?
Can you hear my voice clearly?
あ、で、
あ、音声の共有。
オーディオ、
あ、オーディオ。
オーディオの、スピーカーでもオーディオがいかないなんか選択肢がないな。
最悪これじゃダメですかね。
それだとちょっとっていう。スピーカーはここに置かないんだ。でもシステムと同じしかない。なんでだいいよ。今であれが言ってたのがなぜ来ないなぜ来ない待てよ。
We have some problem with the sounds. You can turn off now the camera. Can you hear my voice?
Not clearly. It's kind of buzzing.
Okay. 自分もだよな。はい。
なんか、他の音って出せます。まあいいや、これで。そもそも置かないな。パソコン問題はい。こっちに繋いでるだけは普通に言って、音は言ってて、音流れてて、このパソコンだとダメ？
そんなことあるんですかね。こっちでズーム入ると。Elif, you can turn off the camera now if you want.
お借りします。
はい、ごめんなさい。はい。
これをすると、来る。ダメそうですね、これ。
来てる。じゃあこっちでズーム入りますか？
ちょっと、そうですね。
はいはい。
それ一応、ここに。
Attention, please. In this room, no drink, no eat. So please, you will put bottle in your bag. You cannot drink anything here in this room.
ID。
So please hide. Please hide somewhere. Otherwise, if we somebody
120-2304。
for us.
1935。で、パスコードが、名前なんで、それ、名前です。なんでも大丈夫です。
Okay, please take your seats. We are starting the second and last session of midnight presentations. The first presenter is from Stellenbosch University in South Africa. And the mission name, presentation name is Stellenbosch Lunar Interferometric Network for Quasi-Static Imaging. Team, okay, you are already there. Please.
Good afternoon. We will present our proposal for Slinky, a radio astronomy constellation mission based in low lunar orbit. Members, which include myself, Rustem, and the main objective of the mission is to perform low frequency radiation. Interference from terrestrial missions is significant and greatly limits Earth-based astronomy. Furthermore, 15 distortions or equals of interest. Our proposed solution is a satellite performing low-frequency radio astronomy on a low lunar orbit. Since a fixed orbit, the moon is shielded the satellites from possible noise sources like the Earth. Other satellite missions have proposed a similar solution, with, however, due to the long wavelengths, they're very limited in resolution, and therefore we propose a constellation mission. So due to the nature of the orbit, there will be a wide range of possible science missions. Primary objectives include observing heliospheric radio emissions, particularly long wavelength sections from solar storms, type 2 and 3 bursts, and coronal mass. Furthermore, we're interested in planetary emissions, particularly from Jupiter, Saturn, and Uranus. Objectives also include acting as a pathfinder mission to test the feasibility of measurements from deep space sources. These may include pulsars, supernovae, black holes, as well as phenomena. Although this may not be achievable, we aim to evaluate practical and technical feasibility for future expansion. It may also include characterizing the effects of scattering on the baseline length at low frequencies, as well as noise sources present in low lunar orbit. The concept operation initially involves two 6U CubeSats in the low lunar polar orbit, with possible future expansion of the constellation. During the period the satellites are shielded from Earth, science measurements will be performed, and when the satellites are in line with sight of the Earth, command downlink, as well as telemetry and data downlink can be done. The communication phase will utilize the NASA Deep Space Network, as will be discussed later. Coordination includes synchronization using onboard atomic clocks, as well as formation control. This will be performed directly to each satellite and not using an inter-satellite link. Shown are some of the key performance parameters for our mission. An angular resolution is targeted 3.9 arc seconds for 10 MHz and 1.3 arc seconds for 30 MHz. This is at the maximum baseline length and is also just a function of the baseline length. To perform accurate interferometry during post-processing, a 1 nanosecond synchronization accuracy is also required. Considering the large data sizes we're expecting, a 2 megabits per second down also required. And target lifetime for the mission is given as 2 years, considering the high cost for lunar missions, as well as the high radiation environment. Pointing accuracy of 1 degree is targeted as a function of the downlink rate required. Accurate payload calibration will also be required due to the propagation of ADCS position estimates, therefore that alone cannot be used. Once again, we'll adhere to the 6U CubeSat specification. The estimate total weight is 7.8 kilograms, which estimate hardware costs about 777,000 Rand.
We will utilize the Zafard SIGU structure with passive thermal control utilizing multi-layer installation as well as wide-coated radiator surfaces. So for the orbit, satellite deployed together in a 100-kilometer low lunar polar orbit. This will provide roughly 72 minutes of Earth communication period per orbit with 46 minutes of science operation. So overflights will increase the phase duration, reduce the baseline length up to a maximum of around 1,600 kilometers. Time satellites are shielded from the Earth can be used for interference down to 14 minutes. The payload on board each satellite is a deployable electromagnetic vector. This is developed by MIT and are currently being deployed on the Aero and Vista missions, which are planned to launch in December this year. This design features vertical wire loop antennas, a horizontal loop, 2 crossed horizontal dipole antennas, as well as a monopole antenna. This combination allows amplitude and phase characterization of the electromagnetic and as well as computation of their covariance terms. So when stowed, the antenna simply occupies only 1 U of volume, but when deployed, the dipole stretch to 4 meters to tip and the monopole 2 meters long. The data acquisition system occupies only a half U of space. After the received 60DC, we utilize an FPGA to perform data filtering, compression, error protection, and data handling. Correlation is performed on ground, but synchronization is maintained with atomic clocks. Data is stored on board a 1 terabyte flash before it is relayed to Earth. So wide band mode is available. However, due to large data rates, this is only used for a short burst. Most of the time will be spent in a narrow band observation mode with additional data reduction. Just on the previous slide. So we also plan to do calibration, which includes internal signal injection as well as external collaboration using well-characterized astronomical sources, which may include Cassiopeia A, Cygnus A, and Virgo A.
Moving on to the communications of our design, we decided to go with the IQ Spacecom X-Link SDR transceiver, which is able to operate from 8 to 8.4 gigahertz. The transceiver is combined with a 4x4 X-band antenna. Given that this setup has a transfer speed from 2 kilobits per second up to 200 megabits per second, we should be able to transfer roughly 1 gigabyte of data in the 72 back directly to Earth. For the ground station, the NASA DSN ground station network will be used. We will be experiencing significant losses during communication periods, as the transmission will be directly from the satellites to Earth, roughly 384,000 kilometers. Thus, use the DSN ground station network as it makes use of high gain antennas which will separate 120 degrees. This will enable speeds of 2 megabits per second for the downlink and 500 kilobits per second for uplink, whenever the satellites are on the Earth side. In summary, a summary of the link budget can be seen on the slide, which includes the transmitter power, antenna gain, free space loss downlink, data link downlink, and link margin, which is 6.8 dB for downlink, 41.9 dB for uplink. To power the satellite, Endura EPS2+ in combination with 2 Endura deployable 6U solar arrays per satellite. The solar array will generate a maximum of 38.4 watt, which will be used to recharge the battery. The satellite should consume an average of 15.6 watt, with the most power consumed by the transmitter. Can be seen from the summarized power budget, the estimated depth of discharge is about 86.03%, which seems very conservative. However, during the lunar eclipse, the satellite is expected to be in total darkness for force, which the EPS should be able to handle comfortably.
Okay, as for the OBC, we chose this specific one, the EnduraSat OBC2, because of its reliability and performance as well as its space heritage. It also has enough headroom for all our onboard calculations. And for the ADCS, we included the cube wheel pyramid stack, and as well as the pocket rocket from SSP thrusters, will be capable of 10 to 200 micronewtons of thrust, as well as specific impulse of 700 seconds. As for the sensors, we're going to use the Southern Ogera star tracker that allows us less than 9 arc seconds of accuracy, and we're also going to use with the combination of the CubeSpace fine sun sensors with a field of view of 170 degrees. And we also have the CubeSpace Cube computer where we're going to implement our ADCS system on, especially the Lunar algorithm, which also includes the MEMS gyros. As for space environment testing, the purpose for this is to ensure that the satellites can withstand the harsh conditions in space. This includes flight acceptance testing, vibration testing, thermal vacuum testing, payload characterization in anechoic chambers, and electromagnetic compatibility tests. Critical electronics and components are verified to ensure reliable operation in space. Last slide. As you can see on our Gantt chart, the development and phase, the manufacturing phase will last about 2 years. And thereafter, the operation of the satellites will also last another 2 years, where it then enters its end-of-life cycle. And we also listed our main risks in this risk register. And as you can see, the mission success relies heavily on the payload data being successfully processed and sent back to Earth, not that much on the radiation damage. Thank you. Arigato.
Okay, thank you very much. And I'm interested in the synchronization, time synchronization. So the 2 satellite has the 1 nanosecond time synchronization requirement, is it right?
Yeah.
And that can be realized by the CSAC only, or you don't need to make some laser communication or something like that in order to realize that? No?
Yeah. So especially for this design, I didn't really consider inter-satellite link. So we're planning to use calibration of the sensors themselves while the phase separation is small of celestial bodies to try and calibrate the sensors in terms of external sources. And using atomic clocks, we should be able to keep that synchronization, otherwise relying on commands from back to Earth to try and keep synchronization.
Okay, so the not only doing such kind of the calibration before launch, but after the launch, you will occasionally do such kind of the calibration, right?
Correct.
Okay, good.
You've done some analysis of the periods where you can do the radio frequency signal detections and communications to the ground, to Earth. But it seems to me that you haven't really looked into your orbital plane change over a lunar month, because sometimes you can see the Earth constantly in your orbit, and sometimes you have maximum eclipse periods. Did you analyze that fully or not yet?
Yeah, so we didn't include that for the simulations, but we did just consider that in the design. So yeah, of course, it's a 3-body problem. There's other sources as well emitting radio, like Jupiter and Saturn, and they will all have an effect on the satellite. So at this point, we're considering, as the orbital plane changes, we're adjusting the mission objectives. So for example, when the Earth is in view and it's less radio quiet, for example, we could look at more nearby, stronger sources like Jupiter, for example, or even solar emissions. However, when there are optimal time where shielded from both the sun and Earth, which also do occur, we could look at more distant sources, especially when the baseline is large.
Okay, I've asked this question already, but how are you going to manage the momentum on the wheels?
Yeah, so originally,
3 thrusters.
Yeah, originally we just had 3 thrusters, and that is to acknowledge that were probably enough. So we designed for 3 perpendicular thrusters, but we acknowledge there will probably be a positional drift with that if you try and do momentum dumping. So yeah, there will definitely need to be 3 more thrusters.
Thank you for that nice presentation. I also have a question about attitude. So you deploy these very large structures from the satellite, which presumably increases the rotational inertia. So have you considered whether the ADCS can cope with such potentially big inertia once you've deployed those structures?
Yeah, so luckily the structures that we're deploying, there are the solar panels which are quite large, but for the payload themselves, it's just essentially a thin carbon tube deployed like a tape measure. So the inertia should be relatively small still. However, we are using a large pyramid for the reaction. We'll try and account for that as well.
Thank you for the presentation. Just coming to your project timeline and the costs. You've got $5 million assigned to deployment and orbital insertion. I just wonder if you could explain what that's covering, because in the mission requirements, you're not accountable for the the lunar transfer.
I think initially we did know about we didn't have to take into account that we need to do the orbital transfers and stuff, but we just thought about like adding that as an extra margin. Also, as you can see, the operation, we added quite a hefty estimate of cost of $10 million USD. Basically, it's just to account for all the collaboration with the external companies, as well as some things we didn't take into account, issues that may arise during operation. But as for your question, yeah, I think it was just because we wanted to add that as extra.
Okay, yeah. So you can, I think you can more or less remove that. So that's good news. For the final cost there, the operations, 10 million. Are there particular? Is there something in there that's particularly heavy in driving that?
There's not something specific, but working with the Deep Space Network with NASA, that's quite expensive, and the goal is to make it a long-term mission. So if it's possible to extend it and doing more and more missions, that will obviously increase the cost of operating the satellites. So that was the main reason for it. It's a rough estimate. It's not anything specific, but yeah, it's the best that we could figure out.
Okay. Thank you.
Thank you so much.
Well, we have plenty of time if you want to continue asking questions. Yes, are you using chip scale atomic clock?
Right.
Are you using chip scale atomic clock on your mission? No, I just heard something like that.
Yeah, that is correct.
They are problematic.
Yeah, it's the microchip SA45S CSEC.
I might just want to add to that as we specifically added this atomic clock for the interferometry data to be timestamped for processing once it's downlinked to Earth.
I have a short question. So in the paper you mentioned passive thermal control will be used. Did you confirm through simulation that that will be sufficient, or how did you come to that conclusion that passive is good enough?
Yeah, so that was not derived from simulation. We kind of went with our instinct with that one. I think we'll probably have to do a more thorough thermal analysis once we have more information, especially for payload. I think is the most thermal critical system. However, since it's still somewhat experimental and we don't really have information from MIT on that yet, that will require further investigation.
Okay, thank you very much then. So our next presenter, that's the third team from the University of Sydney, Australia. And the name of the mission is Lunatics. Please. Okay, start please.
Good afternoon, everyone, and thank you so much for having us. Today we're presenting our mission, Lunar Atmospheric Investigations with Qubits, also known as Lunatics. We're a team of 7 multidisciplinary graduate engineers from the University of Sydney in Australia, and together we worked on developing the Lunatics mission, constructing and testing a smaller prototype CubeSat for Earth orbit, which you can see just down here. We'll pass it around later. The Apollo missions in the 1970s confirmed scientists' previous predictions that the moon has a very thin atmosphere or exosphere. And since then, we've measured its basic elemental composition and overall atmospheric density, but it's a pretty low detail. And what our missions are to gather is more specific details, like whether there's an elemental distribution and an atmospheric density model. The information from our mission will be crucial given humanity's imminent return to the moon, from infrastructure design, greater simulation accuracy for satellite or missions, and potential business and opportunities.
So Lunatics aims to improve the scientific understanding of the lunar exosphere through developing a robust atmospheric model through quantitative results. So to do this, we have 3 main mission objectives in order of priority. The first being to map the distribution of gaseous elements in the lunar exosphere. The second is to develop a mathematical model of atmosphere density versus altitude. And finally, to determine the relationship between it. So to do this, we'll be using 2 6U CubeSats, each with 3 specific instruments. So we've got the ultraviolet visible light spectrometer, the neutral mass spectrometer, and a dust sensor. Moving on to the concept of operations, we'll start with launch from Earth, and this will be aboard the Artemis Space Launch System. From here, we move to stage 2, where we deploy into our lunar orbit via the Dhruva Space 6U deployer. Stages 3 and 4 represent our constant orbit data collection, and this is done using an NMS sensors previously mentioned. While in orbit, we'll maintain continuous communication with our ground station. Then we begin our deorbit phase, at which point we'll be using the dust sensor to collect various altitudes, and finally we'll make contact with the moon to end our mission. To evaluate the success of this mission, there are 3 factors which will significantly influence the success. The first being system stability. This is all about maintaining operational temperature so that our payload can operate successfully. Secondly, we've got pointing accuracy. We need to maintain a pointing vector of approximately 0.15 degrees. This is to ensure our data is valid. And finally, we need to make sure our satellites stay in the desired orbit so that we can cover the entire 29 days.
So here's the chassis from CNC Aluminium 6061. It was chosen because it's widely used in space applications due to its optimized strength and weight properties. So this is just a simplified 2-unit CubeSat design in ANSYS to assess the structural response under launch-like conditions. The transient structural solver was used as a constant 13G quasi-static array. Modal analysis was performed to identify the first 6 natural frequencies and mode shapes, forming the basis for both harmonic response simulations and random vibration analysis. Shock loading uses a response spectrum solver in conjunction with modal results. And as you can see in red is where the largest deformation takes place and was used to help with design decisions. So to mitigate the issue, the top and bottom plates are joined to the frame. This creates a continuous direct load path. There are also other design considerations like release mechanisms and staffs.
Both CubeSats will hold 3 nodes, which will work in conjunction to fulfill the 3 mission objectives. The UV-Vis spectrometer will observe wavelengths, the spectral emission range of the key gaseous elements already detected in the lunar exosphere. Every element has a unique absorption and emission line based on the spacing of its energy levels and hence has a fingerprint that we can use to identify it. By taking a spectrum across the entire atmosphere, we can map the presence of certain elements and observe their distributions, kind of like a mock model made in the top right corner. Both CubeSats will also carry a neutral mass which can detect and measure different isotopes and ions of elements. Additional information and add another level of detail to the aforementioned map, as we can break down the elements into their isotopic distributions and absolute concentrations. The dust sensor will operate independently, detecting the size and density of dust particles through piezoelectric sensors on a film that extends out to the CubeSat side. This payload will only be deployed upon deorbiting, allowing for measurements to be taken at varying orbital radii. and hence we can determine a model for atmospheric density versus altitude.
The cyclic thermal analysis simulated the CubeSat's temperature in orbit ranging from -40 to 80 degrees Celsius. It is conducted in vacuum, so the model only included convection, so no convection. As shown, the outer nose has the highest temperature, while internal is warm and cooled more slowly due to thermal inertia. A separate thermal bakeout test held the CubeSat at 80 degrees Celsius for 3 hours. AZ93 white thermal control coating, mylar layers, capped on control tape will be used as thermal controls.
The XACT50 package from Blue Canyon will be used for determination. It includes determination algorithms, sun sensors, IMU, gyroscope, and star trackers. This will provide a pointing accuracy of 0.003 degrees. Calculate that the total expected external disturbances are approximately 57 micronewton meters. This will be counteracted by the control wheels included in the package. For detumbling of the satellite and desaturation of the wheels, two backhoe propulsion systems, cold gas thrusters will be used. Both of these thrusters combined can provide a total of 38.2 meter per second delta V.
For communication, there's two things we need to consider, which is the uplink and the downlink. For the uplink, we're going to be using the near Earth network of ground stations, and specifically because we're in a team, we want to use the one in Dongara, Western Australia. And so this has lunar legacy and also operates in the X-band, which is desirable for us. For the downlink, we're going with the Boeing Phantom Work deployable high gain antenna, which gives us 25 decibels of gain. This will be directly connected to JPL's Iris transponder, which is a 4-watt transmitter. It downloads at 32 kilobytes per second. It's in the X-band, and we're going to be using BPSK modulation for this. Some calculations for the budgets, and you can see that we clearly have enough budget for both the uplink and the downlink. For the OBC, for our motherboard, we're going with the Raspberry Pi 02W. This will be directly connected to our peripherals through the PCB stack, which we've designed in our 2U, but we hope to extend in our 6U configuration. For radiation, we've decided to use NASA's Z shielding and protect from single upset events as well as long-term radiation damage.
The electrical power system will consist of a power regulation and distribution board, side with solar arrays, and a lithium-ion battery pack. The nanopower P80 EPS will manage power generation, voltage regulation, and protection of the power buses with efficiency around 90%. The BP8 battery pack will be used for energy storage, which contains 8 cells for an 80 watt-hour capacity. Each solar cell produces 1.14 watts at end of life applications, and with 7 cells on the short side and 16 on the wide side of the 6U structure, we can produce a maximum of 18.5 watts with power production of 12.3. This is our power budget in the key operating modes of idle, pointing, science, and transmission. During transmission with max transponder power, we're consuming 18.0 watts, but with a fully charged battery, even in eclipse conditions, this can be sustained for over 4 hours. Circular low lunar orbit with a perilunar and apolunar of 100 kilometers will be used. The circular orbit allows us to obtain repeated measurements at the same altitude. They will each have an inclination of 90 degrees and a period of around 2 hours. Delta V impulses are required for station keeping to ensure the CubeSat remains at a constant altitude. We estimate the required Delta V at 10.9 meters per second, far below our budgeted 38.2 meters per second.
Our project will be split into 4 phases. Phase A is proof of concept. Phase B, assembly integration, which is concurrent with testing in phase C, and then finally mission in phase D. The CubeSat will be prototyped at the University of Sydney, with the final build being done at the Australian National University, where there's thermal, vibration, and thruster testing. And we'll be our mission will serve to increase humanity's understanding of lunar atmosphere and provide opportunities for future commercial endeavors and space missions. Thank you.
Well, thanks. Minutes. Questions, please.
So thank you very much. So would you please explain again why the research about atmosphere of the moon is important?
So obviously humanity is going back to the moon and we're going to go essentially there to stay. That's kind of the plan. So in order to understand the effects on what that could do to infrastructure on the ground, and then also if we're going to have satellites orbit the moon, it's very important for us to have a very robust model atmosphere to really be as accurate as possible with our simulations to kind of mitigate the frantic fixing of things on fly during missions. And we have a lot of this for the Earth and it's very useful, but we don't have as much for the moon. So if we can get this done early before we put presence on the moon, it'd be very, very good.
Thank you for the presentation. The power and the cost budget is very first order. So I think it needs a bit more analysis, more detail, more motivation. Why the specific power budget sufficient and cost budget as well.
For the power budget, what are you referring to? Specific like eclipse times and
yes,
depth of change?
the numbers in there is just rough numbers.
Yeah, it's a pretty rough first pass at the moment, so it definitely needs a bit more refinement.
Yeah, okay, that's your power, but where's the solar panels?
The power generation is just listed in the total power
at
generation.
the bottom, okay.
Bottom, yeah.
And that shows you that you still have some margin available.
Yeah.
Except for the science mission. No, for the pointing and transmission missions you don't have an idle and science.
Yeah.
You have a bit of margin. Okay, I might have missed this table in your paper.
Thanks for the nice presentation. I like your logo and the name. So yeah, very nice work. And I had a question about the orbit. So one of your objectives is to measure density at different altitudes, but you have a circular orbit, right? So in an eccentric orbit would give you access to density at a wider range of altitudes. So I'm wondering why you went with a circular orbit rather than an eccentric orbit.
I think primarily our primary mission objective is mainly the map of elements, and the atmospheric density was something we tacked on the end to kind of kill two birds with one stone when we're deorbiting. So when we do our controlled deorbit from 100 kilometers down to the ground, we're going to deploy the dust sensor, so we will be getting measurements there. In terms of stuff beyond, that's probably stuff for a future mission. And I think as well in terms of the limitations of the mission. I think it's keeping, because we wanted to prioritize the elemental map, so we wanted to have that at a consistent altitude. That was our primary goal.
Okay, so you have the one wing, solar cells, right? Solar panel is just one wing. Yeah. One wing. There is no, how to say, asymmetrical solar arrays, right?
No, it's just I found a paper from a previous CubeSat mission that was, I think it was for in between Earth and the moon or around the asteroid belt that had a dust sensor that just flicked out to one side. So that was what that was inspired by.
Only one side.
Yes.
Yeah. In that case, maybe the solar radiation pressure, internal angular momentum. Yeah, and maybe you need to do a desaturation more frequently. So is there, that kind of the discussion is made for making this kind of before deciding this kind of the one wing?
Yeah, and I think our determination has a lot of leeway in terms of the corrections that we can make as well. So we have a bit of wriggle room in the solar radiation pressure in the orbit to be a bit spinny.
Especially since we have quite a short mission timeline of only 29 days, we have lots of room for station keeping with those effects.
Yes, that wing that you show there is your dust detector. That's not your solar panel. You have mounted solar panels. Yeah, so you only have a body mounted solar panel on the 6U facet and on the 3U facet. It's only two solar panels. Was there on the back side a solar panel as
that's
well?
just the reveal side.
Body
It's on-
mounted solar panels.
It's on all sides.
Yeah, so that will alleviate the problem of solar radiation pressure. I just saw in your paper, your power budget in the paper is different to the power budget you showed in the slides here. So you must replace the one in the one in the slides.
Okay.
Yeah, that one is very rudimentary in the paper.
Yeah, apologies for that.
Yeah, I have a question. So, how do you plan to separate the orbits of two CubeSats by 120 degrees in right ascension of ascending node?
That's a great question, but we haven't actually looked into that. Because of the mission requirements, we looked at post-deployment, and so we didn't get a chance to look at that. But if we were to do the mission, we would look into that in more detail.
Sorry, two CubeSats will propel by itself to place their orbit in.
So we would deploy them at different times so that they would be deployed with a 120-degree right ascension difference.
It's also okay if they're on the same orbit as well. In terms of making our mission, it just meant the mission would be a little bit longer if they were on the same orbit. By having them separated, we can kind of do things that overlap a little bit more and over a shorter time span.
I had a question about the mass of the antenna. I think in the article it says it weighs 23 grams, but it seems to be quite a big structure. So I wanted to confirm how much does this structure weigh?
Sure. I think we can go to the slide. I need to look into it, but I think this image does make it look quite larger than it actually is. So that connects to a 1U unit there. So I'm not exactly sure what the exact materials are that it uses. I might have to look into that more to check the precise mass, but following from that article, I'm not sure what it would be.
We do also have some leeway in our overall mass budget. We're about 1.8 kgs under the requirement for 12U. I mean 6U, sorry.
In your paper, you cite it as being 1 kilogram.
I think there might have been a misalignment there.
All right,
So-
okay. There isn't a picture of that antenna installed or deployed on the spacecraft. Where exactly would that be?
Good question. I believe on one of the bottom sides of the bottom faces. There would be room. We don't have it in the images here. We don't have it expanded, but I believe when we have it in the orbit, it stays within the aircraft and then it becomes it goes out. So
It will deploy from that smaller, from one of those smaller faces.
yeah, I believe one of the
So when it's deployed, do you foresee any attitude control or management issues?
yeah, that'd be another thing we need to consider. But I think the attitude module that we have is very robust.
Okay. And just finally, just to complement that, the dust collector, what sort of nest?
Good question.
It's kind of was more of a this doesn't really exist in real space. We'd have to develop it specifically for this CubeSat. I think I might have written it down somewhere that I read. I think the paper that I read that inspired this, I think they cited the approximate mass of it there, and I think I put that in the paper. I'd have to double check. I can't remember off the top of my head. But
Okay.
I think but because we have such leeway with our budget, I think we should be okay. And I think we can change the size of it. If we do go over the mass, we can then reduce the size of the dust sensor, which wouldn't give us, but it would still be within tons.
Everything deployed, it could be a set of inertia. Or,
Yeah, that was another part. The dynamics of this were a bit, so we kind of didn't want to. I'm just doing a dynamic thing.
The devil's a detail, but
Yeah, I know it's annoying, but yeah.
thank you.
Make it like
We have to stop. One last question. Okay.
Just the previous slide, if you just go back one slide. Yes, this FEA and results, that's not in your paper. I haven't seen it. My question is, why is the maximum stresses there on the of your PCB and not at all fastening point?
We simulated it on like multiple different like points. For just that section, we did put it at that like corner on that point at the edge.
Force there, and you measure what is the.
Yeah, I put this here because it had the largest stress, which is like the most like the biggest issue, which is why I wanted to show it on here, and then how we mitigated that with like load, like connecting the bottom a lot better.
Okay, but it's not in your paper. This slide is, the information on this slide is not in your paper. Make sure that your paper corresponds to the slides you're presenting here.
Yeah.
Okay, thank you very much. Now, our first presentation from Middle East Technical University today, it's going to be a video presentation.
To our students, we would like to present our work on lunar rovers in mission idea contest. And to begin with, we would like to sincerely apologize from you to not be there physically, but we are going to present our title, titled with a conceptual design approach for multi-rover lunar exploration mission in Mauritius. I, Elifur Makkainer, and my teammate Yunus Özdemir, we would like to present our work today. You can see the table of contents here. We have actually 8 subtopics, and we will go through all of them in detail. First of all, while deciding our mission and our design perspectives, we have actually researched on many papers regarding the lunar skylights. We chose these lunar skylights as their features on the geological history of Moon and their possibility of being a future human habitation. And they also have a nature shielding against harsh and difficult conditions of the Moon surface, which will give us more information regarding the Moon's physiology. And we can see that the first paper regarding these lunar skylights, or lava tubes, you can say, are based on the Selene mission, which was written in 2009. And we have decided to take a consideration into these lava tubes, specifically on the Mauritius region. And we have divided our mission steps into 2, which the first one was an actual investigation of the area near the Mauritius region, and as the second step, entering this lava tube to gain more information regarding what's inside of the actually geological feature. And we have decided to move on with the multi-rover system because it brings lots of benefits both in engineering and budget-related perspectives. As you can see, for the first, we have 3 different payload configurations, and this would help us to have more rovers to conduct more experiments. And for the second one, we have observed that having only one rover would cost us lots of weight and volume. And in that perspective, for a multi-rover system, we can actually minimize this weight distribution. And for the third one, while having a cost, mass, and cost budget systems, we have seen that we can actually pay less for a multi-rover system. And for the fourth one, we increase the chance of survivability inside of lab tube entering for having more than one rover. For the mission objectives, you can see 5 of them here. For the first one, we wanted to conduct a 3D mapping structure with a higher resolution. And for the second one, we would like to increase our autonomous driving skills, which conclude in having more skills regarding the control engineering part. And for the third one, we wanted to gain measurements upon temperature and radiation inside or near the Myosys region, which will help us to gain more information regarding possible habitational features. For the fourth and fifth one, we wanted to know more about the moon's geological history as well as its own conditions currently. So magnetic survey and detection of seismic events will help us to learn more about the moon's phases as well.
And for the mission requirements, we have four topics. And the first one is multi-rover coordination and data fusion. As my teammate mentioned, our first mission objective is high resolution 3D mapping inside the lava tubes. To achieve that, we need to have multi-rover coordination. And also, because of that, we need to have a data fusion. And the second one is rover mobility and terrain passableness. As she mentioned, we need to survive inside the lava tube, and due to the skylight entrance is full of rocks and have a dangerous terrain, rovers need to navigate inside the lava tube. And the third one is, as I mentioned, lava interiors entry survivability. And the fourth one is the autonomous navigation and mapping accuracy. We need to have high-resolution 3D map inside the lava tubes to really understand what is going on inside the lava tubes. And to achieve that, we need to have autonomous navigation. And we can continue with the concept of operations for mission. We have four structurally identical small rivers, which approximately weighs around 0.5 kilograms. And they are all equipped with LiDAR sensors for navigation and also the higher mapping. And continuing with the payload, each rover have a special payload for their mission objective. As you can see here, first one is Mag rover, which has a magnetometer inside of it. And the second one is SACE rover, which has a seismometer inside. And the third one is ENVI rover, which has thermal and radiation sensors. And the fourth one is COM rover, which is a relay between the rovers inside the lava tube and between the lander. And you can see the mission phases. First, as my teammate mentioned, we have a first surface reconnaissance around the Myosys region, and then rovers will enter the lava tube via the skylight entrance. And then each rover will start their exploration phase inside the lava tube. And then we are having a data relay. And when the command comes, they dispose themselves inside the skylight entrance. And you can see figuratively the mission phase. Each rover is communicating between Mag rover, SIS rover, and ENVI rover. And SIS rover is sending the data to COM rover to have a relay between the lander and the three subterranean rovers. And we have four mission radio interfaces. First is rover-to-rover communication. As I mentioned in the figure, three of the rovers inside is communicating between themselves to achieve navigation and localization inside the lava tube. And the second one is rover-to-COM rover. As I mentioned, we are having a relay between three subterranean rovers and COM rover. And COM rover is sending the data, payload data, high amount of data to lander, and lander sends to Earth, basically. And you can see the classification of our interface. Each rover uses ultra-wideband for localization purposes. Due to its high amount of data, we have X-band IFO2 to send the payload data to COM rover. And COM rover is sending the data to lander via X-band 2. Each of the rovers is equipped with X-band, and 3 of the rovers are using ultra-wideband for localization, and lander communicates to Earth using X-band or K-band.
For the design perspective, we have measured our rover's actually conceptual design as these dimensions you can see here. And for the durability, we chose a material of which we can we can hold lots of amount of loads there. So we chose an initial layer as for carbon fiber composite, and then we need to actually absorb the shock, which would be taken from any kind of impacts on in the lava tubes deep heights. And for this case, we chose a material named sorbotan, which will help us to absorb this amount of shock. And for the thermal protection system, we believe that the thermal paints will be beneficial for us to having as a third layer on the rover surface, and gives that kind of structure gives us both durability as well as thermal protection. And you can see here are drawings from computer assisted drawing parts. And this one is actually rover. You can see the back and front pages, front views of those. And for the other rovers, Mag rover, SACER, and Envy rover, you can see the payloads there as cameras, and they contain their antennas as well on top of them. Overall, we can say that this mission proposal and design concept gives us an initial frame to work more on these kind of missions, because as engineers, we wanted to learn more about these lunar skylines, and this mission gives us a chance to further research upon these topics as well. And this mission also gives some insightful and actually more materialistic way to provide data about what we can learn regarding the geological features of the moon as well. You can see our references listed here as well. And we will be happy to answer any questions that will be coming from you. Thank you for your attention and your time as well.
Okay.
We're happy to answer your questions.
Is there connection?
Thank you for the nice presentation. I hope you can hear me. And I have a question about the seismic activity measurement. You mentioned that your rovers are equipped with dampers and shock absorption, and I'm wondering if that could conflict with your seismic measurement objective. If all your vibrations are damped by your shock absorption system, maybe you can't measure the seismic activity effectively. So I'm wondering if that's something that you have considered and how you're going to deal with that.
I can answer that. Thank you for your question, first of all. It's actually a good question. Yes, it will affect the measurements according to the seismic units, because the overall material.
So I think, sorry to interrupt you, but we actually can't hear you at the moment. We're just going to check the sound setting. Can you try to speak again?
Can you hear my voice clearly now?
Now.
Can you hear us? Can you hear us? Can you hear us?
Yes, we can.
Can you speak?
Can you hear my voice?
Yes, we can hear you.
Okay. I may continue with the question now. Thank you for asking that kind of question because it's crucial to fully determine the mission objectives. And in shock absorption case, we need that kind of a structure to actually enter the lava tube inside of it. Our first mission was to successfully land inside these lunar skylights, and then if we can handle the all the communication system and all other interfaces, we can continue with the payload part for that. But during these seismic measurements, it would affect the accuracy of the measurements because the material would also give some errors due to the correlations. And for that solution, we may choose to use Sorboten in particular cases of the structure. For instance, not on the inner structure, but maybe on the reaction wheels part. We can come up with that kind of a solution, and we can give an error percentage to our measurements in that case. Thank you.
Thank you.
Can you explain the use of the reaction wheels inside the rover? It's not clear to me what the reaction wheels are doing. And do you really need 3 wheels? I know the rover only only have 2 wheels to roll over the surface, but you only need 1 wheel to maintain sort of attitude of the payload on the rover? Why do you need 3 wheels?
Would you like to answer that?
Thank you for this question. Can you hear me well? During the entry to the lunar skylights, with coordination with our advisor teachers, to maintain the safe attitude to absorb the shock wave, it would be best to have 2 reaction wheels and inside the lava tubes to navigate with dangerous conditions. We said that 2 reaction wheels would be the best choice for us. If I explain correctly.
How is the reaction wheels mounted? Are they orthogonal? It's not clear to me what the purpose is of the 2 reaction wheels in that sense. Because to maintain attitude while dropping down in the lava tube, you can use 1 momentum wheel. You don't need 2 wheels. 1 momentum wheel will give you the stability to land on the propulsion wheels at the bottom of the lava tube. And to maintain attitude in 1 axis, you can only use 1 wheel for that. You don't need 2 wheels. There's something I don't understand about the 2-wheel setup. So if you can explain the 2-wheel setup.
Since we don't know the exact location where we start to enter the lava tube, the lunar rovers may slip or fall indifferent than we expected. So maybe lunar rovers will fall like this or like this. So I thought that maybe instead of 1 wheel, we use 2 wheels. If I explained correctly.
Okay, thank you very much, team. Okay. The next presentation is by the University of Tokyo, Japan. And the title is Lunar CubeSat Mission Concept for Treat. CubeSat Mission Concept for Treat, okay. Please start.
So, good afternoon, everyone. Today I'm honored to present our CubeSat mission concept Treat, the receiver exploring the dark ages. This project is a collaborative effort among several Japanese institutions, including the University of Tokyo, NAOJ, and other collaborative universities. So after the Big Bang, the universe was filled with neutral hydrogen gas. The hydrogen emits and absorbs radio waves at the wavelength of 21 centimeters. And as the universe expanded afterwards, the signal became redshifted, now appearing at much lower frequencies. And this 21 centimeter signal is almost the only way to cosmic dark ages and witness the birth of the first stars. However, unfortunately, measuring the faint signal from the ground is extremely difficult. First, the ionosphere reflects or distorts radio waves, blocking signals from the dark ages. Second, man-made radio interference such as FM radio and satellite EMI, like Starlink, contaminates the frequency band that we would like to observe. As a result, Earth-based radio observation cannot achieve the sensitivity or cleanness required to detect the global 21 signal reliably. However, the lunar far side derives the most unique solution. Unlike Earth, the moon has no almost has no ionosphere. Its activity is very low, and its far side is naturally shielded from terrestrial radio emissions. A few projects worldwide have proposed or tested low-frequency lunar radio experiments, and these missions propose two different methods, which is on-orbit observations and observations of the lunar surface. However, these missions have not been fully realized. Therefore, our main scientific goal is to observe the global 21-centimeter signal from the lunar far side. There are three main features of this mission. One is an on-orbit observation, especially observation on low lunar orbit, LLO. And the second is using small satellite, the size of a CubeSat. And the third is using a variable length dipole antenna for the observation. The full success criterion accumulate 1,500 hours of total observation time, enough to detect the cosmic dawn signal. So the orbit is designed to ensure both radio quietness and long-term stability. At an altitude of 100 kilometers, we achieve more than minus 90 decibels of Earth radio, shielding over 100 degrees in the lunar far side. The orbit has a parallel balloon altitude of 100 kilometers with an inclination of 80 degrees, which maintains a quasi-frozen condition. This orbit was designed ideal simulation beginning from 2030, February 10th, incorporating the effects of solar gravity, 8th degree Earth gravity field, and 48th degree lunar gravity field using NASA fields from this data. It is observed that the parallel altitude remains relatively stable over the propagation period. And this orbit allows TREE to achieve the long duration observations needed to detect such a weak signal. This orbit provides the total observation time of 112 hours, which exceeds the 6,000 hours required for extra success criteria, ensuring sufficient margin and demonstrating the capability to maintain orbit and conduct observations. This mission alternates between two modes every orbit, which takes less than 2 hours. During the far side pass, the spacecraft enters the observation mode, performing telemetry, downlink, command uplink, and occasional data downlink. Additionally, as a when it moves to the near side, it switches to communication mode. Additionally, as a submission, we plan to demonstrate an optical navigation method called a star occultation method, using the precise timing of a star disappearances behind the moon to improve orbit determination accuracy. In the previous slide, we assumed that the satellite would periodically move behind the moon's quite far side. However, since the moon itself hits the Earth, the satellite may follow an orbit where it remains visible from Earth at all times. In such a case, the operation pattern shown earlier would not be feasible. To address this, we developed an operation plan based on one fuller lunar revolution, which is about 27.3 days. As illustrated here, for about 8 days within this period, cannot access optimal far side region. During those intervals, the mission will primarily conduct data downlink and maintenance operations. For the remaining time, when the spacecraft enters the far side quiet zone, it will carry out the 21-centimeter signal observation.
And now introduce the site design of TREE. TREE is designed as a wide 8U CubeSat weighing about 13 kilograms. It operates in the X-band and has a lifetime of up to 4 years. And this is the structure design. The structure frame follows the established, ensuring easy integration with subsystems and launch adapters. Structure analysis under vertical line conditions was conducted. The result shows that the first natural frequency is well above the requirement and providing sufficient margin against vibration and static growth. Okay, for attitude control, TREE uses the exact 100 module with reaction wheels, a stretcher curve, and some sensors for precise pointing. The reaction control system uses a PVR-10 water resist jet. This clean propellant system is safe to handle in the laboratory conditions. And the reaction wheel unloading is performed every 3.5 days, and the LCS per point mass is 0.8 kilograms. Okay, it's a power system. The power system consists of solar panels as power unit, power control unit, and lithium-ion batteries. The solar panels generate about 111 watt at the life and decreasing to 93 watt at the end of life. The storage capacity is 112 watt hour, sufficient to support long X-band downlinks. The next, communication. 3D uses the X-band for communication, low gain for nominal operations, and middle gain for okay. For mission link. The link budget has been online across 54 meter and 13.5 meter ground stations, ensuring liquid margins for data transition. Okay, thermal design. Thermal analysis was conducted using a 6-node model. Both the worst cold case and hot case were analyzed, and multiple heaters with a total power of 10 watts maintain the battery temperature between 10 and 45 degrees Celsius. The payload is viable when sighted. Yes, its length can actually change depending on the observation frequency. It's made volume copper with shape memory properties and uses a complex type structure that allows deployment and redirection by motor control. This flexibility enables the antenna to achieve the optimal length for each observation frequency. In other words, the optimal length for each cosmic era. So this is one of the features of satellite. Next, I'll explain the risk analysis of TREAD. One major risk is EMI interference from the bus system, which could contaminate the low-frequency radio observations. Another critical risk is antenna deployment failure, since the antenna is essential for our mission. So both issues will be carefully addressed and validated through ground testing. And further concern is unintentional radio emission from other lunar missions. As lunar activity increases, the first side of the moon may no longer be completely radio quiet. So our implementation is important. Okay, finally, the mission lies on a shared transport vehicle for lunar injection, which requires careful coordination and flexibility. To maintain or adjust its orbit after separation, TREAD uses 4 CS nozzles capable of performing small orbital maneuvers. Okay, next, the implementation plan. We, the Indigenous Space System Laboratory, are responsible for the satellite Earth design, and NAOJ, National Astronomical of Japan, and other collaborating universities focus on the scientific payload. So total mission cost to be around $3 million, covering the entire development and testing. The project follows a 4-year development schedule, progressing from proof of concept to prototype model. Okay, finally, this is the conclusion. TREAD aims to detect the global 20 centimeter signal, a key probe of early universe, by observing at the radio quiet lunar first site. The site design will operate in a stable low lunar orbit for 1 to 4 years, making long-term observation possible. Feasibility has been validated through the system analysis. So we believe that TREAD, the receiver exploring dark edges, will open window to the early through the power of small satellites. Thank you for listening.
Okay, questions, please.
I have asked this question to other teams as well. Your momentum unloading of your 3 wheels, how are you going to do that with 4 thrusters?
Thank you for your question. I believe that it is possible to do with 4 thrusters, since the variable with the reaction wheels, we have the plus x minus x plus x minus. So there's 6 in total, and we have a RCS thruster with the degree at a certain degree. So there is so we can solve the equation, because there are 8 possible possible maneuvers with these thrusters. Because by using 4 thrusters in different angles, it's possible to solve using simultaneous equations. And also, to give you an example, we have done this actually in past laboratory mission.
Okay, where's the drawing of your satellite showing the axes, the X, Y, and Z? In the paper, there's a drawing on figure 9. You have it in your presentation, that one. Where's the X-axis of your satellite? Oh, there it is in the corner. I can't see it behind the lectrum. I can't see it. Okay. You said in your paper, the X-axis moment of inertia is the largest. In the paper, it says at one point, X-axis moment of inertia is the largest. That should actually be the smallest if you look at your axis definition. The Z-axis should be the largest. If you look at the mass distribution around your center of mass, the Z-axis.
Yes, maybe we have made it.
Calculation of the direction interval is that in a Z-axis or Z-axis. Yes, the worst case is 3.1.
Okay, your disturbance torque analysis is also very first order in the paper. I mean you look at maximum gravity gradient torque, for example, and then you size the wheels according to the maximum torque that you can experience. Solar radiation pressure will also change as you go around in the orbit and as you rotate your solar panels to track the sun. So to evaluate disturbance torques and size the wheels is to do a simulation. Cannot just do a one single back of the matchbox calculation. It doesn't work that way.
Yes. Yes. Thank you very much for your comment.
Thank you for the presentation. Your paper and the presentation, you cite that for your antennas, the mechanism can extend and retract the antennas. Is there a need in the mission or an intention to retract the antennas in the mission?
Thank you for the question. Is there a question asking is it necessary to retract the antennas? Thank you very much. Well, that is a very good question. It is possible to only have a function of deployment, but since we have, so we want to cover the full success first. We want to measure like different. Can you go back to the? So this is the full success. We want to accumulate 1,500 hours for 100 each for 100 hours each for the 50 to 120 megahertz. So we would like to do that first to cover all the frequencies for the 21 global signals. And after that, we have in our orbit assumption, we have 7,912 hours in total. And after that, we would like to retract and do the same measurements with longer observation time.
I see. Okay. And it's always necessary to do that in that order as well.
For meaning the order, what do you mean?
The sequence of observations of the various wavelengths. You always follow that sequence.
Yes, we would always follow that sequence.
And when you return to a given length for a particular wavelength, how accurately that extension? Therefore, how sort of error is are you on repeatable? Is the extension?
That is a very good question, and we are currently considering that development right now with NAOJ, and that is the most difficult part, I believe, and we have not been able to demonstrate it actually, but we have been working on it with NAOJ, and also we have been there have been research doing these retractable, not antennas, but retractable dipoles in JAXA ISS, and we are talking to the professor with to realize accuracy for the length of the dipole antennas.
Have you analyzed? I mean, you could probably quite trivially analyze the positioning control, the length control that you need to establish that. Have you looked at that yet?
Oh, we have not done yet.
No. Okay.
Thank you very much.
Okay.
Thank you for the nice presentation. I have a question about the time with sustained Earth visibility. So this is quite a long time, so 9 days, 4 days, 9 days. So have you considered doing kind of secondary objective during that 4-day period? So now it's just for mission downlink, but could you do some additional science during that time as well?
Oh yes, our additional submission is the star occultation method, the new mission method. So during that time, we're going to test how the star occultation method works, because it has not been done precisely on the orbit. So that is our submission during the phases when communication in both observations is not necessary. Thank you very much.
Any further questions?
This sky average 21 centimeters. What is the frequency of that signal?
Thank you very much. The frequency of the signal differs between the era which we want to observe, since it is redshift from the 21 centimeters. So
okay, so it's over various.
It's various
frequency
yes,
range
yes.
from
So,
10 to 120
yes,
megahertz.
yes. That's why we want to change the length of the dipole antenna.
So it's not a single frequency.
Oh yes,
so.
that is the new point of our mission.
Okay, thank you very much. Now, the last team to present today is from Kyushu Institute of Technology, and the name of the mission is Vista PIPR. Please. Okay, start, please.
Okay, good afternoon, everyone. So we are from Kyushu Institute of Technology. We are from Space Robotics Lab. So so this is our team. So I am Abdullahil Kafi, and our team is very diverse. We are from I am from Bangladesh. We have a member from Japan, and also we have member from Mexico. So our mission is very simple. We will search water in the space. So why water is important? So in the morning, we already know that from CEO of iSpace, they said that water is very important for the space. So if you want to build anything, we need water in the space. So that's why we are targeting the water, and that's why we are targeting in the darker area side of the lunar area. So we have actually 5 mission objectives. Some is to find the hydrogen element, so which actually correlates with the water. And next, so immersive VR model. So why it is important? So in the future Artemis mission and anything, so we need that area's images and with a very high resolution. That's why we are creating the digital twin version of our the South Pole area, and then validate our drill excavation system and survey. So during that, so we will survey with our rover. Our target is a little bit greater than 500 meter. And last one is the autonomous system demonstration. So we are targeting that one too. So after that, my team will continue for the next one.
Okay, the rover is compact, just 35 centimeters long and under 10 kilograms in mass. Despite its size, it's equipped with 4-wheel drive and steering, rocker suspension, and specialized blasters that let it handle slopes up to 25 degrees. At its heart is an NVIDIA Jetson Nano, a small but powerful computer running ROS2. It processes radar and camera data in real time, using them to help the rover perceive its environment and navigate autonomously. It's basically a self-thinking, self-navigating robotics geologist. On the mast, a 120 megapixel panoramic camera and a 32-channel 3D LiDAR. Together, they build high-resolution terrain models. And what truly makes this rover special are its instruments. A miniature neutron spectrometer that detects hydrogen, a near-infrared spectrometer that confirms water molecules, and a compact drill that can reach 30 centimeters into the regolith. Collected samples are heated in a tiny oven. If water vapor or hydroxyl appears, we can measure it directly. In one small package, we have detection, confirmation, and extraction all at once. The rover uses an aluminum honeycomb chassis designed from aerospace engineering. It's extremely light yet strong. We analyzed its behavior under extreme stress up to 10G from different directions. Even under side loads, the honeycomb keeps its stiffness while saving weight. This strength to weight balance lets us add more instruments without exceeding 10 kilograms, a big advantage for lunar rideshare missions.
Powering the rover is still also producing about 30 watt-hour per peak. We also have 64 watt-hour lithium battery to operate during low sun period. Since the mission is only during lunar daylight, we don't need to survive frozen lunar night. The rover consumes around 10 watt-hour per day, so even modest sunlight produces ample energy margin. For communication, data travel via UHF to lander, then by X-band relay to Earth. This setup allows up 6 gigabytes of science data to be sent home, including all panorama and LiDAR point cloud. Once deployed from lander, the rover begins a 6-step cycle. First, after initializing the system, the rover performs an initial scan to create a baseline map. Next, it starts navigate short segment while constantly analyzing hazards using the sensor. At each stop, it conducts detailed survey to refine the 3D digital twin. Then it searches for hydrogen using a Newton spectrometer. If the readings are promising, the rover will collect and heat up sample to test for water release using NIRS. Finally, data is transmitted via LUN. This process repeats multiple sites over 40 days, gradually building rich scientific and visual map. We chose the rim of Shackleton crater at the lunar South Pole as our landing site. This location uniquely combines about 12 days of continuous sunlight with nearby PSR believed to hold ancient ice. It's also a scientifically valuable candidate for Artemis landings. This survey not only helps us learn about lunar volatiles, but also make the region safer for future human mission.
The impact of Vista Pippa goes well beyond one rover. We are opening the moon to the public through immersive VR built from real mission data, letting anyone experience Shackleton's limbs as if they were there. Technically, we demonstrate AI-driven autonomy, light-weight neutron sensing, and high-resolution mapping. Key technology is essential for the Artemis era. By using off-the-shelf component and open source software, we lower the cost for university and new space nations, making lunar exploration accessible to all. Of course, every mission carries risk, but we planned it carefully for the key ones. If the LiDAR fails, stereo vision takes over. If communication drops, the lander relay at the data rate and the beacon can still send health data directly to us. If power becomes limited, incline solar panels and daytime operation keep the rover running. Redundant sampling system and flexible software ensure the mission can continue without losing critical data. This slide shows the Vista Pippa budget. The total is about $4 million, mainly for hardware, testing, personnel. This project follows a 36-month development plan. Here, we focus on defining requirements and building early predictables. Phase 2 focus on subsystem design and the development of our VR-based digital twin simulator, leading up to the preliminary design review. Phase 3, we fabricate and integrate the engineering model, test autonomy software on the Jetson computer, and complete the critical design review. We will complete full-scale environmental testing before integration with the commercial lander. Next, let's take a look at the demo video.
So this is just a simulation, how we created the our target. So first, the lunar rover will go to the place, and then it will perform its mission. With the in the upper part, you can see the LiDAR and camera, and here how we plan to and collect the things, and so that's all from our part. Thank you very much.
Okay, just perfect timing. Questions, please.
In your paper, thank you for the presentation. Nice slides. In the paper, you talk about a tilted solar panel. What is the reason for that? And can you adjust the tilt angle continuously or track the sun, for example?
Yeah, okay. So if you see the South Pole, we have a very low angle of sun. So during the mission, sometimes if we put because there is lots of shadow area. So if our rover goes to a very shadow area, so we can have that option to tilt the things and have the sunlight more onto our solar panel. So that was the primary reason behind this. Is it answered?
That's good. You want to look for water ice with your rover, but you also want to be in the sun. Doesn't the two things contradict each other?
Sorry, so it's not always in the sun because we target the Shackleton rim area. So mostly our target is we want to finish everything within the daylight. So it will first, when in the concept of operation, it will land, it will traverse a little bit, and then it will go to the darker area to find the things. In the Shackleton rim, if you see, so it's 50% of shadow and 50% of lunar light, with a very low angle. So that's what target is, the Shackleton rim area. So there will be a lighter person. We want to survey those actually near about 500 meters to find water. So it's not only in the dark area. So we want to search in those areas. That's our target.
Okay, thank you very much. And I'd like to ask you about how to navigate your rovers. The first question. And second question is, what will be the maximum DOD of the battery during the nighttime?
So we will not operate in the nighttime. So that's the like maybe in the shadow, but not in the nighttime. So our primary target, we want to finish everything within the 14 days, which is like one lunar.
Just 40 days. Yeah.
14.
Yeah. Oh, okay. 14 days.
Yes.
Okay. Okay. And how about the first one? Navigation.
Navigation. We have the LiDAR one. So for 3D point cloud. So for mostly we use, if you see in the front side, we also have the depth camera. So with that one, we try to create the point cloud as surrounding of the rover. And with our like the mast size, we have only like 8 meters of like area that we can't see with the LiDAR. But if you use at least those LiDAR point cloud, we can easily navigate. Not easily, but we have some like, we already have this kind of SLAM navigation tools because we will use ROS system. And in ROS system, if you can integrate the LiDAR and the real sense, it can be possible. And in ground is already proven, but not in space.
Okay. So then if this rover finds the water and the rover wants to tell the position of the water to us, how it can do it?
So it has is like in the real 3D real sense, it has its own IMU. So when it moves, so it also can detect its own position. So our target is like we will not have exactly like this is the position we get the water, but at least we will have some idea. So in this area we have water. So that's our target.
What will be the rough rate? What will be the accuracy of the positioning? It's several meters or several tens of the meter.
Sensei, like with the real sense, they like it's totally cost product. So they say this within the like 0.1 meter they can give us the position.
0.1 meter.
Yeah, with the real sense.
Great. Yeah. Okay, thank you very much.
It's not our technology. It's like already like the real have those.
The IMU will give you your rotations, your angles. It will not give you any distance, the accelerometers is not sensitive enough. The noise levels are too high. But the rate sensors also will have bias. So if you integrate the bias of the rates, then you get wrong angles over time. So IMU on its own will not really tell you over a long period of time what is the true direction of the rover.
For that, we have the 3D point cloud. So when the rover landed, so initially it will take a 3D point cloud. So with the 3D point cloud, we know exactly like how from the starting point how far we can go. So that's our target.
Okay. And you measure the distance also by the rotations of the wheels, that they can spin, that they can...
We didn't target right now that, but we can also put, because the problem is it's very small. With that small size, we are like facing problem how we can compact everything. That's why like actually they did a very excellent job. You know, the Japanese people can compact everything in a very small place. So we tried to compact everything, whatever we can, we compact that thing inside this rover. So that
small wheels on a rough terrain is very tricky.
Yes, and so that's why we if you see our like model, we have a very different kind of wheel, not the usual wheel. Sorry, it's a little bit. So if you see the inside of our wheel, so we have some to make it very lighter. Sorry. So you can see we have a spiral kind of thing. So like in one of presentations, Sensei asked a question, how it will drill the thing, right? So in our case, we first excavate by our wheel and go inside and then drill. So it will not like pop up in the air. So that's our target. So that's why we design the wheel in that way. And also there is like grouser. So if you see, we have a little bit grouser. We also try to implement grouser things on the like rover wheel. So to have like more friction with the to the surface.
Hi, thank you for the presentation. Very beautiful.
Thank you very much.
So in terms of the drill and the heating chamber, so if I understand, you drill your sample and then you drop it into the heating chamber, and it's at the heating chamber where you make your measurements. Is that correct? There's nothing in the drill that's making measurements.
Yes.
Okay.
So, oh, yeah, please. Sorry.
So my question is, have you considered what heating effects you'll get from the drill on the sample during drilling? And if that's going to be sufficient for some evaporation and therefore loss of the material you're then going to try to detect?
Yeah. So that's the most trickiest part in our like whole mission. So initially we are still doing research on particular on that system, but we are having NIR, like near spectrometer system on top of the here. So this one. So this is our chamber. So it will go inside and this oven will heat up. Then this actually with this NIR system, we will try to detect the wavelength, like the changes, because if the water evaporate, so the NIR system will detect the wavelength in a different like I forgot the actual value. It's around 3 micrometer, right? So yeah, if you got something in that 3 micrometer range, that means like it has maybe some water, but that's the target right now. So that's how we win the system.
Forgive me. I mean evaporation during drilling.
No. So during drilling, we will just collect only the soil or maybe very hard sample of soil.
Mm-hmm.
So then it will put it inside here.
But you're not interested in anything that's going to evaporate from that. Is that correct?
Right now, no.
Okay.
So because we build the chamber inside, because we need to heat up, because in the Shackleton rim area is very cold.
Yes.
So that's why we need to put it inside like an oven, and then we heat up.
Okay. So it's negligible, any losses that you get from drilling.
Yes. So we are not considering that part right now.
All right. Thank you.
Thank you.
Thank you very much. Now we have half an hour break. After the break, we have an excellent presentation from the finalist of MIG-1 by Masashi Kamagawa. So be here at 17:15, and at 17:30, the results will be declared and there will be award ceremony. Okay, enjoy your break.
Have a real purpose, something we have to create. We contribute to the groundwork of humanity's future by creating a sustainable, growing presence and infrastructure in space. The cislunar economy. Utilizing water resources on the moon is essential to expand human activity in cislunar space and benefit life on Earth in a sustainable way. iSpace is at the forefront of exploring and utilizing this precious resource. iSpace provides the most comprehensive lunar transportation service on the market, transporting and operating payloads in lunar orbit and on the surface. We are laying the groundwork for human presence on the moon, offering services around water resources, energy, communication, and data about the lunar environment to commercial customers, as well as governments and academic institutions. iSpace offers an entry point for innovative technologies to be verified and operated on the moon. We are able to iterate quickly, finding the most cost-effective solutions for the unique obstacles of the moon. iSpace makes possible what has previously not been possible. We pave the way towards an economic system that can not only sustain lunar development, but also return value to humanity and Earth. We are committed to secure humanity's future on Earth and beyond. And so we invite you to join this new cislunar ecosystem. Join us on our lunar quest. Expand our planet, expand our future for all humankind.
Okay, everybody, please have your seats. So we have a post-mic finalist presentation. The presenter is Masashi Kama from University of Shizuoka. And I think you will be telling which MIG and such. Was it the first MIG? The Mission Idea Contest? Second, okay. Oh, okay, good. Okay, and I think we can start. Floor is yours.
Thank you very much. So I'm very happy to present our satellite development story in front of the MIC finalists. So this is our current the satellite. So name is Prelude. The Prelude is some kind of the music in the. It means this is a precursor of the earthquake. Can be detected by the satellite. This is the idea. Then, so let me introduce myself. So my background is not satellite development. So my research is to understand some of the precursors to predict or give the information of the forecast for the such kind of the various natural disasters using electromagnetic observations, in particular earthquake and tsunami and lightning, the volcanic eruption, the breeze. And so I use the various instruments. So for example, of course, the satellite, and so balloon and the drone, recently drone. And so location is the Mount Fuji, the highest mountain in Japan. In this world hit small island, Ogasawara, in very beautiful islands in the isolated island, and this is Antarctica. Then, so my concern is natural disaster mitigation. This is one of the list of the number of the deaths caused by natural disaster during the recent 20 years. This is the percentage. The largest one is inland earthquake. Of course, once earthquake in the inland, sometimes the building collapsed, and lots of the people are dead by the building corruption. And also tsunami. Most of the tsunami is generated by the earthquake. So it means almost half of them, of the natural disaster, is caused by earthquake only. So it means earthquake prediction is very, very important for the natural disaster mitigations. However, so we have lots of disaster caused by earthquake, but so present earthquake prediction is almost meaningless in the helplessness. So it means earthquake suddenly occurs for us at this moment. Then, but so short-term earthquake, this is important for us. But so the obviously provides a disaster mechanism. If we can do that, it's very good. And so it means it requires precursor detection because the short-term earthquake prediction requires precursor of the earthquake. Then the several 10 years ago, French Demeter satellite, this is the CNES first microsatellite, launched it in 2004, or 6 years. Then this is a observation in the low Earth orbit. Then one of the several reports mentioned that the statistic in the analysis maybe this kind of the atmospheric electron enhancement occurs this region 4 hours before the earthquake. Then this it means if this kind of the electrical density enhancement in the locally, it means some of the lightning signal is absorbed here, this part, because this is the electrodensity enhancement and natural particle also large. It means the absorption of the electromagnetic waves occurs here. So if we observe electromagnetic field in the satellite altitude and compare here like this one, we can understand the precursor existence. Then, so Demeter has some of the instrument. So they have the electric field measurement here. They have the 4 booms for the electric field. They have the probe here. So if we measure the potential difference between these here, we can understand the electromagnetic field like here. So this is the Demeter satellite in the this satellite.
Très vite, le générateur solaire est déployé.
So this is the first satellite of the CNES. This one. The advantage of the satellite observation for this kind of the precursor is like this one. So for the statistical observation, statistical analysis, this kind of the precursor and precursor lasts for the 4 hours. It means, for example, satellite in the move like here, so it is easy to observe this kind of the precursors. So we have many earthquakes or globally. It means satellite can understand this kind of the precursors, and also we can apply the statistical analysis easily. Then the history of our satellite development like this one, the key person is Rei Kawashima-san. Maybe everybody knows that. So the first motivation is like this one. Very old age, and more than almost in the 20 years ago, Kawashima-san, no, I was presented this kind of the studies in some of the Japan Space Writer Club. This club is for the writers and journalists and some of the artists, something like that. So I presented the ionospheric precursor studies here. Then Kawashima-san remembered this kind of my presentation. So surprisingly, first week, so during the mix presentation, large Tohoku earthquake occurs. So Tohoku earthquake is the northern part of the Tokyo, but so the building, very strong motion occurred here. Then this is a very significant, severe disasters. You know that. Then Kawashima-san interviewed the feasibility of the earthquake prediction using a small satellite to me. This is almost 1 year later. Then she recommended, and I should submit the MIC2. But unfortunately, at this moment, I have no idea to develop the satellite itself. I don't know the reaction foil, and I don't know the geomagnetic torque or something like that. So Kawashima-san invited 2 specialists, Kikuko Miyata, Professor Kikuko Miyata, and Kohei Tanaka. So they support me. Then we got the second prize of the MIC2. Then the title of my presentation is the project of microsatellite constellation for the earthquake study. And also, I participated in the MIC4. I designed, integrated this satellite. Then so little bit mature satellite design. So I also got the second prize in MIC4. Then after that, this is the idea base. After that, Kawashima-san also introduced Professor Masahiko Yamazaki. He's over there. You know that he's development of the Heptasat. This is the virtual satellite for the education. So she introduced him. Then so Professor Yamazaki and I decided to develop the real satellite for the earthquake-proof satellite based on the MiG-2, the MiG-4 designs. Then we started so-called Prelude satellite. After that, our proposal is accepted by JAXA Innovative Satellite Technology Demonstration. So it is for the JAXA supported the launching opportunity. Then we have a chance to get the launching using the rocket. Then maybe within 6 months in the end of this fiscal year in Japan, so Prelude will be launched by the Electron rocket. This is the rocket, not JAXA rocket, but so because you know that the JAXA rocket is not so good at this moment. So here, they both, and I'm sorry that this is a malfault. This is not a good thing. Then JAXA decided to vote this Electron rocket, so we will launch by the Electrons. Then, so we expect in the Prelude will be operated for 2 years. So let me introduce the MiG design. This is a very baby design in the poor knowledge of the satellite design. So this one. So we designed the microsatellite. So this is the main satellite. We have the 3 boom like this one. We also the sub-satellite in the CubeSat. So this one. So we designed this kind of the orbit. But so problem is like this one. We have no idea to develop the boom. Boom is important of for the measurement of the electric field. But so some of the technicians propose the 3 idea like this one, but not so feasible at this moment. For MiG-4, so I learned how to design the satellite a little bit at this moment. I know that this kind of boom in this kind of bamboo style in the boom like here. So next design is a little bit matured. So we have the 3 probes for the electric field and put also the electro temperature probe here. So these are still microsatellites. It's a little bit larger here. Here. So this is a real feasible one. This is so boom. So we applied this system for this kind of probe. But when we designed the real satellite, so we designed Prelude satellite, much smaller, much smaller. Why the 6U? Here, like this one. So we employed this 2 extended boom. These are conductive. Conductive is important for the electric field measurement. And so we put the 2 probes. Now, this very long distance, almost 3.3 meters. It's good for the resolution of the electric field measurement. Then, and so we employ, this is the electron emitter to keep the satellite potential because the small CubeSat is a very unstable electric potential of the satellite potential. So we have to keep the electric satellite potential. So we use this kind of electron emitters to control the satellite potential. So this is developed by the French group. Then so far, our boom is like this one. This is a little bit feasible, it's a very small one. So maybe you can see this in the ground-based experiment. Yeah. This is a breadboard model. So it takes a very long time to reach this kind of the boom. So I asked lots of companies, local university develop this kind of boom. The mission requirements are quite serious. So we have to keep the conductive. We have to have the long booms. So it's very difficult to finalize this kind of boom. Then the conclusion. So MiG visual in the contest sought just seeds for our real satellite produced. And so UNISEC-Global is the treasure box for the connecting the talented people. Kawashima-san introduced Professor Yamazaki, so we can make a good collaboration. So winning the twice and make, so this is the easier to raise the funds. So we can get the funds in the government and other private foundation. And so this is make support this kind of to get the money. And finally, our president will be scheduled in the early 2026. Then president has a capability of the Earth electromagnetic measurement, which contributes in the space weather and the various natural disaster measurement. So now we are fundraising in the started in for the second period and third period to aiming the build the construction at this moment. So thank you for your attention. So we hope to see your real satellite based on your MIC presentation. Thank you very much.
Thank you very much. Okay, now Professor Nakasuka is going to present the results.
Okay, so it's time to show the result of today's Mission Idea Contest 9. Are you ready? Okay, so we will provide this kind of the 4 awards. And I would like to present the result one by one in this order. The first one is the student prize. Only the student team is, has a chance to get this award. And the IAA award. IAA, Dr. Lena Sander, every time gave us this award to us. And so we'd like to have this award in the second one. And we'll go to the second place and first place. Okay? Okay, first, let me show the result of the student prize. Student prize goes to the Stellenbosch University. Congratulations. Please come up. Okay, so the Professor Funase of the University of Tokyo will give this certificate to you. Please come here.
Yeah, student prize goes to Stellenbosch University, South Africa, for the paper entitled Stellenbosch Lunar Interferometric Network for Quasi-Static Imaging. On the occasion of the 11th UNISEC-Global meeting, November 1st, 2025, in Tokyo. So, congratulations.
Congratulations. And this is more important.
1 year.
How much?
How much?
30? 50,000 US dollars?
No.
Later. But congratulations. Okay, so please wait. So Professor Funase will give you some comments.
Yeah. So so everyone knows that their proposal was well organized and the technical discussion was high level, and also the importance of the mission was very clear. So our review committee recognized that the team deserves the student award. So congratulations.
Okay, thank you very much. Let's move on. The next IAA award. Okay, it is an award given by Dr. Rainer Sander, DLR. Okay, he contributed to this mission idea contest for a long time. And the IAA award goes to it's a National Taipei University of Technology. Congratulations. Please come up. So the certificate will be given by Richard. Okay. Okay, so please get up the podium. Okay.
Thank you very much. Well, the IAA award this year has been awarded on the basis of internal collaboration. And for anyone who's new to UNISEC, you'll soon and very quickly over the coming days learn about the spirit of collaboration in UNISEC. So it's with great pleasure that I give this IAA award to Ying Lao, Yi San, Yan Ling Lai, Hawan Chan, Bu Chinin, Kang Xian Pan, Invisat Yusuf, Nikbat Riaz, Ratnesh Mishra. Congratulations. More comments? Just to embrace the spirit of raised words, I would just like to say, yes, no, go.
Just to share to my
Okay, now the two prize remaining. What's here? All. 全部。Okay. So second place goes to Kyushu Institute of Technology. Congratulations. Please come up. And the certificate will be given by Max.
Thank you. So it's my great honor to award the second place of the 9th Mission Idea Contest to the Moon to Abdullah Hilkafi, Yuzuki Fukata, Taichi Nakamura, Kosuke Iwatsu, Jorge Ruben Casiricano, and Kenji Nagaoka from Kyushu Institute of Technology, Japan, for the paper entitled Vista PIPR, Visual Immersive Sensing and Terrain Analysis for Polar Ice Prospecting Rover Mission. Congratulations. And take a photos, please. Okay. One more. Yeah, and also the very big money. How much? 100,000 Japanese yen. Wow, wonderful. Big money. It's larger than my salary. Congratulations. Good. Okay. So only one prize is remaining. Let us move on to the final one, the first place. First place goes to University of Tokyo team. Congratulations. And the Herman will give you the certificate. Okay. Some comments?
Yes, we actually had no choice because this was really a professional paper with good technical quality. And I would say you could see that 9 people worked together to produce this paper from 7 Japanese universities and 2 institutes in Japan. And that's also collaboration, although not over borders of countries, but inside Japan where UNISEC started. And congratulations with the hard work you put into this. We could see it and it was technically and professionally done. Yeah.
Okay, thank you very much. So this is the all the prize is awarded, and then comment. First, I would like to have a comments from iSpace, who is a kindly sponsor this MIC9. So please give us some comments.
Thank you very much, Nakasuka Sensei. So I'm Masayuki Urata, Senior Manager for Business Development iSpace, and it is our great honor to support this Mission Idea Contest. And actually, so we became a corporate member of UNISEC around 2 years ago, thanks to Kawashima Rei-san. And so at that time, there was a previous Mission Idea Contest, and we discussed, so can we arrange a Lunar-related Mission Idea Contest for next time? So at that time, so I had a little concern, so how many ideas, proposals we will receive. But so it turned out that I think 20 ideas, 25 ideas was submitted. So it means, so I think maybe over 100 students or professionals involved in this Mission Idea Contest, and it is very impressive to iSpace. Yeah. So also, so today I heard, listened many proposals, and they are very impressive. And I would like to convey all proposals, ideas to our engineering team. I believe it will inspiring our engineers as well. So let me do that. And for this time, so we supported some prizes, but unfortunately, it is not enough to fly to the moon. But for the future, so I would like to keep supporting such activities so that some of your team will develop actual payloads, maybe satellite, maybe rover, and fly to the moon together. And also, actually, so we have 3 members, UNISEC alumni, working for iSpace. So we hope so some of you may join iSpace for the future and like a target to the moon and expand our ecosystem to Cislunar together. So we are happy to, how to say, interact with you for the future. So thank you very much.
Yeah, Walata-san, thank you very much for such encouraging words. Thank you very much. Of course, maybe so please consider that in future you will collaborate with iSpace. Please say that to your government. Okay? There is a very, very, very good chance to go to the moon. Okay. So anyway, thank you very much. Okay, so now we'd like to give the finalist certificate to all the teams. And I'd like to say the name of the team and please come up. The first one is the National Central University. Please come up. Okay. And so this is a certificate to participate as one of 10 selected finalists in the oral presentation at the 9th Mission Idea Contest to the Moon. Anyway, thank you very much. Thank you very much. Okay, thank you. Thank you. So the next team is University of Sydney, Australia. The first one is the Serene project team. Please come up. Okay. Yeah. So yeah, this is a Serene team. This is to certificate that you from the University of Sydney participated as one of 10 selected finalists in the oral presentation at 9th Mission Idea Contest to the Moon. Congratulations. Thank you very much. Thank you. Okay. Thank you. So the next one is South Africa team. Duxon, please come up. Okay. So congratulations to be a finalist. Yeah, please try again to get applause. Okay. Thank you. The fourth one is the University of Sydney, Australia again, SAT-GPT. I like this name. SAT-GPT is coming from ChatGPT. So the University of Sydney is the first appearance, and so please continue this effort. And the next time, please aim for the prize. Okay. But anyway, so congratulations to be a finalist. Congratulations. Okay. Thank you. Thank you. Thank you very much. Okay, so the next one is Again, South Africa. Yeah, this is already. There. もう一つ。Okay. Yes. So this team is the University of Sydney, Australia again, Lunar Atmosphere Investigation team. Please come up. Okay. So again, congratulations for becoming the final, finalist, 10 finalists. Okay. So next time, please aim for some prize. Okay. Please continue. That is very important. Congratulations. Thank you very much. And the photo, maybe I think we'd like to take all the participant photo. All the participants for the mic, please come up. Please come here. Finalists, all the finalists. Please come to the podium. Yeah, also Rustem. And also the juries and the MC, Rustem, please come up. Okay.
Reception will start at 6 p.m. So, yeah, after in 5 minutes, we will start reception just there in foyer. Please come.
Hi, everyone. Can I get your attention, please? If everyone could leave their bags in this room, but only take their valuables and make yourselves into the reception, that would be great because there's not enough room for everyone's bags. So please leave them here, only take your valuables and make your way outside. Thank you.